Somewhere beneath your feet, buried under millions of years of rock, could there be the remains of a civilization that built cities, burned fuel, maybe even looked up at the stars just like we do? It sounds like science fiction. It sounds like the kind of thing you'd find in a late-night documentary with dramatic music and grainy footage of Atlantis ruins. But here's the strange part. Serious scientists, actual peer-reviewed researchers at NASA and Rochester University, have asked this exact question. Not because they believe it's true, but because when you really think about it, they couldn't immediately prove it wasn't. This is called the Silurian Hypothesis. And before you picture ancient astronauts or lizard people building pyramids, let's be clear about what this actually is. It's not a claim. It's not evidence of a lost civilization. It's a thought experiment, a scientific exercise in humility. Because if an advanced industrial civilization existed on Earth tens of millions of years before humans, one that rose, built cities, burned fossil fuels, maybe even flew through the sky, and then vanished, would we even be able to find proof of it today? That question forces you to confront something deeply unsettling about time. Not human time, deep time, geological time, the kind of time where 100,000 years is a blink and 1,000,000 years barely registers as a heartbeat. Earth is roughly 4.5 billion years old. Human civilization, all of it. The pyramids, the Roman Empire, the internet, every empire that ever rose and fell. That's maybe 10,000 years. A rounding error, a whisper compared to the shout of deep time. And here's the thing about deep time. It doesn't preserve. It erases. Ocean floors get swallowed back into the Earth's mantle every couple 100 million years through a process called subduction, melted down and recycled like nothing ever happened. Mountains crumble into dust. Sediment buries entire landscapes under miles of rock. Continents themselves drift, collide, and get crushed into unrecognizable shapes. Given enough time, geology doesn't just forget, it actively destroys the evidence. So, if a civilization existed, say, 90 million years ago, back when dinosaurs still walked the Earth, what would actually be left today? Would we recognize a city if we drilled straight through it? Would a skyscraper survive better than a fossilized fern? These are the questions we're going to dig into tonight. Now, if you're listening to this to fall asleep, that's exactly why I make these. So do me a favour, drop a comment telling me where you are and what time it is right now. I love seeing it. Tokyo at midnight, Chicago right before bed, London just settling in for the night. It's oddly comforting knowing people all over the world are drifting off together to the same strange questions about deep time. And if you want to listen without ads, without music interruptions, just smooth, uninterrupted voice guiding you to sleep, follow me on Spotify. It's linked in the description below. While you're there, if you've got 30 seconds, a 5-star review genuinely helps this show reach more people who need it. Okay, settle in. Because tonight we're going to explore what evidence an ancient civilization might actually leave behind, where that evidence might be hiding right now, and whether science can really test something this wild without just making things up as we go. So let's actually define this thing properly, because the name alone tends to send people in the wrong direction. The Silurian Hypothesis takes its name from an old episode of Doctor Who, where reptilian humanoids called Silurians supposedly ruled Earth long before humans existed. And that's a fun bit of trivia, but it's also where a lot of the confusion starts. Because when you hear the word Silurian, your brain jumps straight to lizard people in togas, building temples out of scales and ambition. That is not what we're talking about tonight. The scientists who coined this term, Gavin Schmidt at NASA and Adam Frank at the University of Rochester, borrowed the name as a kind of wink, a nod to science fiction. but the actual question they were asking had nothing to do with reptilian civilizations or ancient astronauts. Here's the real question, stripped down to its bones. If an industrial civilization existed on Earth millions of years before humans, would there be any way for us to detect it today, using the tools of modern geology and chemistry? That's it. That's the whole hypothesis. It's not a claim that such a civilization existed. It's not evidence, it's not even really a theory in the scientific sense, because a theory needs testable predictions and mountains of supporting data. This is something more like a diagnostic tool, a way of stress testing our own methods for reading the rock record. Think of it less like a discovery and more like a fire drill. You're not saying there's definitely a fire. You're asking if there were a fire, would we even notice the smoke? Now, I want to be really clear about what this hypothesis is not, because it gets twisted online constantly, usually by people looking for clicks rather than clarity. This is not a claim that dinosaurs built cities. Nobody serious is suggesting velociraptors had skyscrapers or that triceratops commuted to jobs in stone office buildings. That's not science. That's a cartoon. This is also not proof of aliens visiting Earth in the deep past, and it's definitely not some secret government conspiracy about lost technology buried under Antarctica. I know how tempting that version of the story is, especially late at night when your imagination starts filling in gaps with the wildest possible explanations. But the actual hypothesis is far more restrained and, honestly, far more interesting once you understand what it's really asking. Schmidt and Frank weren't trying to prove something happened. They were trying to figure out something much more unsettling, whether we would even have the ability to prove it either way. And that distinction matters enormously, because most scientific questions start with, here's evidence, let's explain it. This one starts with, here's a scenario, let's see if evidence could survive at all. It's a question about detection limits, not about ancient history. It's asking, what is the resolution of our instruments, geologically speaking? What can slip through the cracks of deep time without leaving a trace we'd recognize? Why would serious researchers, people with NASA affiliations and peer-reviewed publications, spend time on something that sounds, on the surface, like pure speculation? The answer actually connects to something incredibly practical, something with real stakes for how we understand climate change and planetary history right now. Schmidt and Frank were partly motivated by a completely different question, one much closer to home. If human civilization collapsed tomorrow, and I mean truly collapsed, cities empty, industry stopped, no one left to write the history, how would a geologist 10 million years from now know we were ever here? Would there be a signal? Would there be a scar in the rock layers that says something intelligent lived here, something that burned fuel, altered the atmosphere, changed the chemistry of the ocean? And if the answer is yes, if we would leave a detectable signature, then the next logical question becomes obvious. Could something like us have done the same thing before, tens of millions of years earlier, and just gotten erased? This is where the thought experiment becomes less about ancient civilizations and more about humility, scientific humility, the kind that keeps good researchers up at night in a productive way. Because if we can't rule out an ancient industrial civilization using our current tools, that tells us something important about the limits of our knowledge. It's not an admission that one existed. It's an admission that our confidence in saying it didn't exist needs to rest on solid reasoning, not just gut feeling or the absence of obvious ruins. Science, real science, isn't about being certain. It's about knowing exactly how certain you're allowed to be, and why. Now, here's where we need to slow down and get precise, because the word civilization is doing a lot of heavy lifting in this whole conversation, and it means different things depending on how you use it. There's civilization in the broad sense, meaning complex, organized society, groups of individuals cooperating, sharing knowledge, maybe developing agriculture, maybe building permanent settlements. Ants have complex societies. Termite mounds are architectural marvels built by creatures with brains smaller than a grain of rice. Beavers reshape entire landscapes through dam building. None of that requires industrial technology, and none of it would necessarily leave the kind of geological fingerprint we're going to spend the rest of this exploration talking about. Then there's civilization in the industrial sense, meaning a society that has crossed a very specific threshold, the threshold of extracting and burning concentrated energy sources at scale. Coal, oil, natural gas, nuclear fission, anything that lets a species punch far above its biological weight class in terms of energy consumption. This is the kind of civilization the Silurian Hypothesis is really concerned with, because industrial activity leaves chemical signatures that ripple through entire planetary systems. Carbon isotopes shift. Nitrogen cycles get disrupted. Strange new molecules appear in the fossil record that never existed before: plastics, synthetic compounds, radioactive isotopes from nuclear activity. These are the kinds of things that could, in theory, survive for millions of years buried in sediment layers, long after every city, every road, every physical structure has been ground down to dust and swallowed by tectonic plates. So, when we ask, could there have been a civilization before humans, we really need to ask, which kind? A complex society, sure. That's almost certainly happened in some form throughout Earth's long history, in ways we might not even recognize as civilization at all. But an industrial civilization, one that burned fuel the way we do, one that altered the chemistry of the atmosphere and oceans the way we currently are, that's a much narrower and much more testable question. And it's the one Schmidt and Frank were actually interested in. This brings us to the core constraint that shapes everything else we're going to discuss tonight, and it's a concept that sounds simple but has genuinely unsettling implications once you sit with it. Time resolution. Geology doesn't record history the way a historian writes a book with neat chapters and clear timestamps. It records history the way memory works after a long, exhausting year, in fragments, with huge gaps, with entire events compressed into thin, easily overlooked layers, or completely lost altogether. A civilization that lasted even a few thousand years, industrial technological planet altering, might leave a geological signature no thicker than a few centimeters of rock, buried under millions of years of subsequent sediment. Try finding a few centimeters of anomalous rock hidden somewhere across a planet, covered mostly by ocean, shifting continents, and endless cycles of erosion and deposition. It's like trying to find one specific page ripped out of one specific book, except the book has billions of pages, and most of the library burned down millions of years ago. This is preservation bias, and it's brutal. The things most likely to survive across deep time are not delicate objects, not technology, not anything resembling what we'd recognize as artifacts. What survives are broad global chemical signals, changes to isotope ratios in ocean sediment, shifts in atmospheric composition trapped in ancient rock, disruptions to global carbon and nitrogen cycles that show up as thin, unusual layers in geological strata found on multiple continents at the exact same depth, meaning the exact same moment in time. Local evidence, buildings, tools, bones, roads, all of that gets erased with startling efficiency over millions of years. Global evidence, the kind written into the chemistry of the entire planet at once, has a much better chance of leaving something behind. So this is the standard scientists set for themselves when they take this hypothesis seriously. Not can we find a fossilized skyscraper. That's essentially impossible, and expecting it misunderstands how deep time actually works. Instead, the real question becomes, can we find a global chemical anomaly, something that shows up simultaneously in rock layers from different continents, something that looks like it doesn't belong, something that resembles, in structure if not in scale, the kind of chemical fingerprint our own industrial civilization is leaving in the geological record right now in real time, whether we intended to or not. And that right there is the real heart of the Silurian hypothesis. Not a search for ruins, a search for scars. The kind of scars only an entire planet's chemistry could carry, and only a species drilling deep enough and thinking carefully enough would ever notice. To even ask whether a past civilization could hide in Earth's history, we have to understand something uncomfortable about that history. It isn't a clean archive. It's not a carefully labelled museum storage room where every artifact is catalogued and preserved. It's more like a palimpsest, a manuscript that's been written on, scraped off and written over again, billions of times. Earth is not just where history happens, Earth is an active editor of that history. Start with the big eraser, plate tectonics. The ground under your feet is not permanent in any meaningful sense. Continents drift, collide, break apart. Ocean floors are born at mid-ocean ridges where molten rock wells up, then slowly creep away and eventually dive back down into the mantle at subduction zones. Most of the crust beneath the oceans is younger than the dinosaurs. Entire ancient landscapes, with all their sediments and fossils and potential clues, have been quietly fed back into the planet's interior, like paper into a shredder. When a plate is subducted, the rocks that once formed seabeds or coastal plains don't just slip under and sit there intact. They're heated, squeezed, twisted, minerals recrystallize. Original structures are blurred and then erased. That's what geologists call metamorphism. You can still tell these rocks came from somewhere, but the fine details, the delicate fossils, the thin chemical layers, the subtle signatures get overprinted. Imagine taking a hard drive full of data, melting it down, and using the metal to build a new hard drive. On some deep level, the information is still there. But practically it's gone. Even rocks that don't vanish into the mantle aren't safe. The same plate motions that pull crust down also shove other crust up. Uplift raises old seafloors into mountain belts. Once that happens, erosion goes to work. Wind, rain, ice, rivers, all patiently grind the surface down. Valleys deepen, peaks crumble, sediment washes away and gets dumped somewhere else. Over millions of years, a mountain range can be worn almost flat, and the rock that once sat miles underground can be exposed at the surface, stripped of the layers that used to sit on top of it. This is why older rocks are so rare at the surface, and why the ones we do have are often heavily altered. Earth's early history is like a book you've read in the bath too many times. The page is warped, the ink smeared, whole paragraphs illegible. The further back you go, the more you're relying on a few surviving scraps, and those scraps aren't even continuous. Geologists think of sedimentary layers as pages in a history book, but they're pages with huge missing sections. Sediments don't fall evenly everywhere, all the time. They only accumulate in certain environments: lakes, river deltas, deep oceans, floodplains, places where material can settle and not immediately get washed away. Even in those environments, deposition comes in fits and starts. A river might lay down mud for 1,000 years, then cut down through that mud and remove half of it, then switch channels and start building a new stack somewhere else. Those breaks and erasures show up as what geologists call unconformities. You can stand at a cliff and put your hand on a line where the rock below might be hundreds of millions of years older than the rock above, with nothing in between. No gradual transition, no continuous archive, just a jump cut. An entire chapter missing. So when we say the rock record, there's a temptation to imagine a complete run of volumes from Earth, year one to Earth, present day. In reality, it's more like we have a random assortment of volumes from different printings, some pages torn out, others overwritten, with coffee spilled on half of what's left. To pull a story out of that mess, geologists use a toolkit that's equal parts chemistry, physics, and pattern recognition. Radiometric dating lets us measure how long certain isotopes have been decaying inside minerals, turning radioactive clocks into age estimates for rocks. Stratigraphy, the study of layered rocks, lets us line up sequences across regions. If this distinctive ash bed appears here and there, those places were recording the same moment in time. Index fossils, the remains of species that were widespread but short-lived, act like timestamps. Find a particular trilobite in two separate outcrops, and you know those layers are roughly the same age, even if they're on opposite sides of a continent. But even when we can date things, there's another problem: time averaging. A layer of mud a few centimeters thick might represent a year of quiet deposition. Or it might represent 1,000 years of occasional floods, each laying down a thin smear of sediment that later gets compressed into a single band. Shells from animals that lived centuries apart can end up jumbled in the same layer. Chemical signals from brief events, maybe a decade-long pollution spike, get blended with background conditions and smeared out over millennia. The rock record doesn't capture every moment. It takes a long exposure photograph and then compresses it. This matters enormously for something like the Silurian Hypothesis. If an industrial civilization lasted, say, 5,000 years, a blink geologically, its entire existence could be captured in one thin, mixed layer of sediment, or not captured at all in many parts of the world. Local signals might be erased by erosion, bulldozed by glaciers, or buried in basins we haven't drilled yet. What stands the best chance of survival are the broad, stubborn things: global shifts in isotope ratios, strange combinations of elements that don't easily go away, rare synthetic molecules that resist breakdown and get locked into clays or deep-sea muds. In other words, Earth is constantly editing its own history, but it has a bias. It ruthlessly deletes the detailed local stories and occasionally preserves the big global plot twists. If we're going to ask whether a pre-human industrial civilization could have existed, we have to narrow our expectations to the kind of evidence that can actually make it past the editor. Not buildings, not machines, but chemical ghosts written into the stubborn parts of the planet's archive, surviving just long enough for someone curious far in the future to go looking for them. So let's turn the question around. Instead of asking, could an ancient civilization have vanished without a trace? Ask, if we disappeared right now, what traces of us would still be around in 1,000,000 years? 10 million? 100? Because that's really what the Silurian Hypothesis is doing. It's using us as the test case. We're the only industrial civilization we know. So we can take our own world, hit fast forward in our minds, and watch what fades and what stubbornly refuses to go away. Start close to home. Imagine the city or town you live in, a year after humans vanish. Power goes out within days. Water systems fail. Basements flood. Plants begin to reclaim pavement. Within a century, most buildings are collapsing. Steel rusts, concrete cracks, glass shatters, roofs cave in. The glass towers that feel so permanent now would start shedding panels almost immediately. Their skeletons twist and buckle without maintenance. Give it 10,000 years and almost everything built above ground is gone. The tallest skyscrapers are reduced to weird low mounds of rubble. Highways are buried under soil and vegetation. Bridges have fallen. Dams have silted up and eroded. To a geologist wandering around that future landscape, our grand architecture would look like slightly odd hills and oddly straight ridges, if it's visible at all. Electronics vanish even faster. Copper wiring corrodes and is scavenged by chemistry and by whatever life is around. Plastics exposed at the surface crack, crumble, and get ground down into smaller and smaller fragments. Data centers, with their whirring servers and glowing racks, become damp metal skeletons in a matter of decades. The specific information, the movies, the emails, the satellite images are simply gone. There is no geologic archive for bits, but not everything is equal in the face of time. Some of the dirtiest, least glamorous parts of our civilization are actually the most durable. Landfills, for instance, huge mounds of compacted trash covered over with clay and soil. Those are, in geological terms, artificial sedimentary bodies, layers of waste sandwiched between layers of cover material. Over hundreds of thousands of years they'll compress dewater and begin to lithify. A future geologist might find a strange layer full of oddly uniform pebbles of glass, ceramic shards, pig bones, and little flecks of plastic. Not a city, not a monument, a garbage bed, mines and quarries are another kind of long-lived scar. Open-pit mines carve enormous holes into bedrock. Underground mines leave voids and collapsed structures. With time, many will fill in, slump, and be draped by new sediments. But the disrupted stratigraphy, the way once continuous rock layers have been sliced, removed, or backfilled, can remain recognizable for very long periods. Drill through a basin tens of millions of years from now, and you might pass through a chaotic zone of mixed material, enriched in certain ores, unlike the natural patterns above and below. Rivers will also remember us. We've straightened channels, built levees, carved canals, dammed valleys. 1,000,000 years from now, active river courses will have migrated many times. Yet in the buried subsurface, there will be abandoned channels, artificial cut-offs, old reservoir sediments. These can leave a telltale pattern: sudden changes in grain size, trapped pollutants, odd geometries of sand and mud that hint at engineering rather than natural meandering. Subtle, but detectable if you know what you're looking for. Then there are the truly stubborn artifacts, ceramics and some types of glass. Properly buried, a porcelain plate can last for astonishing spans of time. Glass can devitrify, chemically alter, but the silica stays. In archaeological contexts, we regularly recover pottery, tens of thousands of years old, with clear designs still visible. Scale that forward. After 1,000,000 years, designs and glazes are probably gone, but the shards themselves may persist in certain protected environments, deep in landfills, buried in river terraces, locked into lake sediments. Yet even those are still local. A broken mug here, a buried brick there. The further out in time you go, the less likely it is that any specific object survives at all, and the more you have to think in terms of chemistry rather than artifacts. This is where our civilization really leaves its mark, in global geochemical fingerprints. We've mobilized vast amounts of heavy metals, lead, mercury, cadmium, chromium, rare earth elements, and spread them through soils, rivers, and oceans. Some of those metals bind strongly to clays and organic matter and end up buried in marine sediments. Over 1,000,000 years they'll get mixed, diffused, and somewhat diluted. But compared to the natural background, there can still be a detectable pulse, a thin layer where certain elements spike globally. We've also made synthetic organic molecules that never existed before: PCBs, PFAS, complex halogenated compounds. Most of them break down on human timescales, but a fraction will be locked into sediments. Clay minerals and organic-rich muds are very good at preserving weird organics. In a core drilled tens of millions of years from now, a chemist could, in principle, find a narrow interval where these impossible molecules appear, then vanish again. A brief chemical anomaly, but a loud one. Then there are isotopes. By burning fossil carbon at industrial scales, we're driving a rapid shift in the ratios of carbon isotopes in the atmosphere and oceans. Specifically, we're dumping in carbon that is relatively light in carbon-13. That leaves a characteristic wiggle in the carbon isotope record, a negative excursion. We're also altering nitrogen cycles with fertilizer, pushing more bioavailable nitrogen into ecosystems than most natural systems would sustain, which can show up as shifts in nitrogen isotopes in sediments. These isotopic changes are exactly the sort of signal that survives smoothing and time averaging. A brief industrial era smeared out over 1,000 years of mud still looks like a sharp global deviation when you zoom out to million-year scales. Nuclear activity is its own special category. Fallout from atmospheric tests left distinctive radioactive isotopes and their daughter products scattered worldwide. The short-lived ones decay away quickly, but some plutonium and cesium isotopes have half-lives long enough that their decay products will still be measurable for millions of years, frozen in ice cores, soils, and marine clays, at least until those archives are themselves destroyed or altered. A concentrated nuclear war or series of meltdowns would add to that signal. But even then, erosion and subduction slowly dilute and recycle it. After tens of millions of years, it would probably survive, if at all, as a barely perceptible bump in trace element concentrations. So if you roll the tape forward 1,000,000 years, what's left of us isn't a skyline. It isn't a monument visible from orbit. It's a thin, messy horizon in the rocks. Slightly odd sediments where cities and landfills once stood. Disturbed strata where mines once chewed into the crust. A global chemical glitch, spikes in certain metals, flashes of strange organic compounds, abrupt shifts in carbon and nitrogen isotopes. Maybe faintly, the ghost of our nuclear age. Push further into tens or hundreds of millions of years, and almost all of the physical reshaping of the surface is gone, worn flat or shoved into the mantle. But some fraction of those chemical ghosts may still linger in a few surviving basins, trapped in rocks that escaped metamorphism and subduction. And that's the crucial calibration. If that's all our planet would preserve of a global, technologically capable species, even given our intense industrialization, then any search for a pre-human civilization has to be tuned to that level of subtlety. Not for cities, not for statues, for the brief, strange chemical shadows left when a clever animal learns to rearrange the planet and then disappears. Geologists have a nickname for that strange, thin horizon. Our species is busy writing into the rocks. They call it the Anthropocene. Not officially, not yet. There's debate. Some researchers argue it deserves to be a new epoch of geologic time, like the Pleistocene or the Jurassic. Others say it's more like a sharp event inside the existing Holocene. A blip rather than a full chapter. The argument might sound academic, but for the Silurian Hypothesis it's incredibly useful. Because what they're really fighting over is this. Does our industrial moment leave a signal big and weird enough that tens of millions of years from now it stands out to whoever is reading the rocks then? In other words, would we notice us that makes the Anthropocene a kind of template? A model for what a detectable technological civilization looks like when it's boiled down to geology. Look at the candidate markers researchers have proposed. One is plastics. We're making and discarding hundreds of millions of tons of them every year. Microplastics are now found from the tops of mountains to the deepest ocean trenches. In beach sands and lake beds, they settle into sediments as tiny coloured grains. Most of those long-chain polymers will eventually break down, but some fraction gets buried fast in oxygen-poor muds, where chemistry slows to a crawl. Future geologists might not find intact shopping bags, but they could detect odd concentrations of plastic-derived carbon and microscopic fragments embedded in a narrow layer of rock. Another is fly ash, those fine glassy spheres produced by burning coal at power plants. They're light enough to ride the wind across continents, then rain out into soils, lakes, and oceans. Under a microscope, they're unmistakable, perfect little beads of industrial soot. In modern sediments, they already form a clear time marker starting in the mid-20th century. Bury them, compact them, turn them into stone, and you still get a distinctive sprinkling of artificial spherules in one thin band. Concrete is yet another. Humans have become a geological agent of carbonate production. We pour billions of tons of it into foundations, roads, seawalls, tunnels. Most exposed concrete will crumble and erode, but huge volumes are already buried underground parking structures, subway tunnels, building basements. Over long spans they'll chemically alter, but they don't revert to natural bedding. They turn into strange human-made conglomerates, with angular fragments, rebar ghosting as rust stains, voids in odd geometries. A geologist drilling through a former metropolis might pass through tens of meters of this urbanite, a rock type that simply doesn't occur before our time. Then there's the nitrogen story. Synthetic fertilizers have blown open the natural constraints on how much biologically available nitrogen circulates through the biosphere. Rivers carry that excess to the coasts, feeding huge blooms of algae, followed by low-oxygen dead zones when all that organic matter decays. Those events leave paired chemical and biological fingerprints, shifts in nitrogen isotopes locked in organic-rich muds, and fossil assemblages dominated by a few tolerant species. It's a planetary-scale experiment in rewriting the nitrogen cycle, and it shows up in the sediments almost immediately. But having markers isn't enough. For a signal to stand out in deep time, it has to be not just weird, but widespread. A local cement factory leaves a local trace. A single landfill is just a lump. The Anthropocene becomes interesting because many of these markers are genuinely global. Plastics and fly ash in ocean sediments from all over the world. Nitrogen shifts recorded in lakes and coastal margins on multiple continents. A synchronous pulse of new compounds and altered cycles, all packed into a geologically abrupt interval. At the same time, some signals are patchy by nature. Concrete and landfills cluster around cities, reservoir sediments pile up behind dams. These regional features won't form a continuous band around the planet. Instead, they'll appear as scattered anomalies, rapid switches from natural floodplain deposits to fine, uniform dam lake muds, sudden accelerations in sedimentation rates where eroded soils rushed off deforested hill slopes, odd layers of mixed rubble where quarries and construction chewed up and redeposited material. Biology records the shock too. This is where biostratigraphy comes in, the study of how fossil assemblages change through layers of rock. Right now, we're driving what many biologists call the sixth mass extinction. Large animals are declining, specialized species are vanishing. At the same time, a handful of hardy generalists, rats, pigeons, certain weeds, some insects are spreading almost everywhere. Add in crops, livestock, pets, and you get a global reshuffling of who lives where. From the far future that looks like rapid faunal and floral turnover, a sharp boundary where many lineages drop out of the fossil record, while a few suddenly appear in places they never lived before. Shell beds dominated by a couple of pollution-tolerant species, pollen records where diverse forests collapse into simplified, human-favoured plant communities, and then perhaps slowly rediversify after we're gone. Put all of this together and the Anthropocene template starts to take shape. A brief, thin slice of time marked by a carbon isotope shift from fossil fuel burning, nitrogen and phosphorus anomalies from fertilizer use, spikes in certain metals and industrial particles like fly ash. Strange organic molecules and plastic residues, abrupt biological change, extinctions, invasions, homogenization, localized but intense sediment disruptions near former population centers, dams, reservoirs, artificial fill, eroded soils, urban rubble. None of these on their own absolutely require a civilization. Some can be mimicked by volcanism, by asteroid impacts, by natural climate swings, by ocean anoxic events. But the exact combination, the timing, the chemistry, the biological response, the global spread of multiple artificial markers at once, that's what makes the Anthropocene a powerful test pattern. And this is where the Silurian hypothesis leans in. If an industrial interval existed long before us, and if it reached anything like our scale, we shouldn't expect to find its skyscrapers or its tools. We should expect something like an ancient Anthropocene, a narrow slice of rocks showing an odd cocktail of global geochemical shifts, rapid species turnover, and localized sediment chaos. Not a lost city, a lost pattern. To find that pattern, geologists start with one of the cleanest tools they have, the chemistry of carbon itself. Not all carbon atoms are exactly the same. Most are carbon-12. A tiny fraction are carbon-13, which is slightly heavier. Life is picky. Plants, algae, and some microbes prefer the lighter version when they pull CO2 out of the air or water. Over time, that preference leaves a subtle but measurable bias, a kind of accent in the planet's carbon speech. Geochemists write that bias as delta the 13C. Delta 13C. It's just a way of saying, how much does the ratio of carbon-13 to carbon-12 deviate from a standard reference? Tiny differences, measured in parts per thousand. But those tiny differences respond when the carbon cycle is disturbed. Burn a forest, for example, and you release carbon with a particular delta 13C flavor. Dissolve limestone with volcanic CO2, and you get a different one. Each reservoir, deep ocean, surface waters, soils, fossil fuels, has its own characteristic signature. When you shuffle carbon rapidly between those reservoirs, delta the 13C in the atmosphere, and oceans shifts, and that shift is recorded in the shells of marine organisms, in organic matter, in carbonate minerals. Layer by layer, it settles into the sediments. Our civilization is currently running one of the most extreme delta 13C experiments in Earth history. Fossil fuels, oil, coal, natural gas are basically ancient, highly processed plant carbon. Plants are strongly depleted in carbon-13 compared to the atmosphere. They carry a distinctly light delta 13 signal. When we dig that carbon up and burn it, we flood the atmosphere with CO2 that is isotopically light. The result is something called the Suez effect, a clear, measurable decline in atmospheric delta the 13C over the last century or so as fossil fuel CO2 dilutes the natural mix. Ocean delta the 13C follows along as that CO2 dissolves into surface waters and slowly percolates into the deep. From a future geologist's perspective, what we're doing looks like this. An abrupt injection of billions of tons of isotopically light carbon into the atmosphere ocean system over a geologically tiny interval, hundreds of years, maybe a few thousand if you're generous, in sediment cores that shows up as a sharp downward step in delta 13C values, often just a few centimeters thick. But carbon is only half the story. Extra CO2 traps more heat, and that warming leaves its own fingerprints. Here, a different isotope comes into play, oxygen-18, or delta the oat. Water molecules containing the heavier oxygen, 18, evaporate, and condense a bit differently than those with oxygen 16. During cold periods, more of the light oxygen gets locked into ice sheets, and oceans are relatively enriched in oxygen 18. During warm periods, the ice melts, the balance shifts and delta won out in marine carbonates drops. For Aminifera, tiny single-celled organisms with calcium carbonate shells are especially useful. They live in the upper ocean, build their shells from seawater, die and rain down onto the seafloor. Drill into those sediments, measure delta than 8 of 8O in shell after shell, and you get a kind of ancient thermometer. Combine that with delta the 13C, and you can see both carbon cycle disruptions and temperature swings stacked together in time. So if you were hunting for a vanished industrial civilization, one obvious strategy would be to look for delta the 13C and delta 38O events that rhyme with our own, a rapid negative excursion in delta the 13C, a big sudden input of light carbon, paired with evidence for abrupt global warming. The difficulty is that Earth can do similar tricks without any help from industry. Massive volcanic episodes, like flood basalts, can belch huge amounts of CO2 in relatively short bursts. That CO2 often has a different isotopic signature than fossil fuels. But if volcanism cooks buried organic matter or destabilizes methane hydrates in the process, you can still get a pronounced negative delta 13C shift and warming. Likewise, the planet's own climate machinery can occasionally trip and dump vast stores of carbon in a hurry. Methane clathrates, ice-like compounds in ocean sediments that trap methane, can destabilize during warming, releasing methane that later oxidizes to CO2. Methane is extremely depleted in carbon-13, so such releases produce sharp delta the 13C drops, just like burning fossil fuels. Large-scale thawing of permafrost, or the rapid oxidation of buried organic matter can do something similar. On the other side of the ledger, changes in how much organic carbon gets buried can also move delta the 13C around. If, for some reason, the oceans suddenly start burying a lot more organic rich mud, perhaps during an ocean anoxic event, then carbon-12 is preferentially locked away in sediments. The remaining carbon pools become relatively richer in carbon-13, and delta 13C goes up instead of down. All these processes, volcanism, methane release, organic carbon burial, are confounders. They're natural ways to get sharp delta the K8 and delta the 8 excursions without anyone building power plants. So what would make a candidate event suspicious? At least enough to warrant a second look. You'd probably start with an interval where several things happen together. In a relatively thin slice of sediments, representing perhaps tens of thousands of years or less, you'd want to see a rapid global negative delta 13C excursion, indicating a large quick injection of light carbon. Paired warming in delta 3030 and other temperature proxies, not just local changes but a broad, multi-basin signal. A timescale that's unusually fast compared to typical volcanic or tectonic carbon releases, compressed into what, in the rocks, looks like an almost instantaneous chemical pivot. Evidence that the carbon source looks organic, very light isotopes without a clean volcanic fingerprint, like widespread layers of fresh basalt or a global spike in volcanic ash. And ideally, other oddities layered into the same narrow band, shifts in nitrogen cycles, strange metal enrichments, unusual organic molecules. Not just a carbon burp, but a complex, multi-component disturbance. We do in fact see delta the 13C and delta the PHOT of events like this in the ancient record. Some almost certainly are purely natural, others are more ambiguous and hotly debated. A few of the most dramatic ones have already caught the attention of Silurian Hypothesis fans, because they look, in outline, uncomfortably familiar. We'll come back to one of those, the Paleocene-Eocene Thermal Maximum, later. Before that, though, we need to widen the chemical lens beyond carbon to other cycles our civilization is busy rewriting. When geologists widen that lens, one of the first things they notice is that we aren't just rearranging carbon. We're rewriting the planet's basic recipe for life. On Earth, two elements quietly control how much life the surface can support: nitrogen and phosphorus. Think of them as the throttles on the global food web. Add more of them in the right form, and ecosystems rev up. Take them away, and everything slows down. For most of Earth history, those throttles have been set by geology and microbes. Nitrogen in the atmosphere is plentiful, but it's stubborn. Most organisms can't use it directly. You need specialized bacteria and archaea to fix it, turning N2 gas into biologically useful forms like ammonia and nitrate. Phosphorus, meanwhile, is locked up in rocks. It gets released slowly by weathering, carried to the oceans by rivers, and recycled again and again through organisms and sediments. It's often the ultimate limiting nutrient, the thing that, once you run out of it, stops further growth no matter how much nitrogen and sunlight you still have. Then industrial agriculture arrived, and those ancient limits stopped applying. In the early 20th century, a couple of chemists figured out how to break nitrogen's stubbornness on an industrial scale. The Haber-Bosch process takes atmospheric nitrogen, runs it through high temperature and pressure in the presence of a catalyst, and spits out ammonia, ready-made fertilizer. From the planet's point of view, this is astonishing. In just a bit more than a century, humans have roughly doubled the amount of biologically available nitrogen entering the land surface each year. What used to be governed by slow microbial metabolism and thunderstorms is now dominated by factories and fertilizer spreaders. That artificial nitrogen doesn't just stay in the soil. Plants use some of it, some is lost as gas, but a huge fraction leaches into streams and rivers, carrying a distinctive chemical whisper. Like carbon, nitrogen comes in multiple stable isotopes, mainly nitrogen-14 and nitrogen-15. Natural processes, nitrogen fixation by microbes, nitrification, denitrification, sort those isotopes in characteristic ways. Fertilizer production, intensive agriculture, and the way we apply and recycle manure all tweak that balance. Modern sediments, lake cores, and coastal muds already show it. Shifts in delta-13 the nitrogen isotope ratio, tracking the expansion of industrial agriculture. In some places you see a sharp drop in delta-5 net in organic matter right when synthetic fertilizer use takes off, as fields and rivers fill with nitrogen that's been stripped of the heavier isotope. In others, you see more complex patterns as denitrification and wastewater treatment play their part. From the perspective of deep time, what matters isn't the exact direction of the shift in every single basin. It's the coherence, a global near-synchronous disturbance of the nitrogen cycle, marked by unusual delta-15 signals in sediments, formed over a short interval and linked to other changes. Because when you overfeed ecosystems with nitrogen and phosphorus together, another fingerprint appears: eutrophication. You've probably heard of dead zones in modern oceans, places like the Gulf of Mexico where fertilizer runoff from rivers fuels massive algal blooms. The algae grow explosively, die and sink. Microbes eating that dead material suck the oxygen out of the water. Fish and shellfish flee or suffocate. In severe cases, bottom waters become anoxic, completely devoid of oxygen. Anoxia leaves marks. In low oxygen or no oxygen conditions, different minerals form, different microbes dominate, and organic matter is preserved rather than fully decomposed. Over time, this builds up distinctive layers of dark, organic, rich mud. Within those layers, the microfossils change. Certain kinds of algae, cyanobacteria, and tiny plankton that love nutrient-rich stratified waters become more common. Others adapted to clearer, well-mixed oxygenated seas decline. The assemblage of foraminifera, the same little-shelled organisms we used for carbon and oxygen, shifts towards species that tolerate low oxygen or episodic stress. Under the microscope, it looks like a sudden reorganization of the plankton community. In the chemistry, you see spikes in organic carbon, changes in trace metals like molybdenum and uranium that respond to oxygen levels, and often those telltale D5 excursions tied to intense nitrogen cycling in oxygen-poor waters. Phosphorus is wrapped into this story too, because phosphorus is so often the limiting nutrient. Any process that rapidly increases its availability can supercharge productivity. Modern civilization does this in two main ways. First, by mining concentrated phosphate deposits, ancient guano piles, marine phosphorites, and spreading that phosphorus onto fields thousands of kilometers away. Second, by eroding soils much faster than natural rates through industrial farming, deforestation, and construction. From the planet's point of view, that looks like a pulse, a geologically sudden transfer of phosphorus from a few localized rock reservoirs into the global surface water cycle. Rivers carry the excess downstream, lakes and coastal zones record it as layers enriched in phosphorus, relative to older and younger sediments, often paired with evidence of high productivity and low oxygen. Over millions of years, some of that moved phosphorus can even get locked into new phosphorite deposits, concentrated in particular horizons that future geologists could measure and date. So, if a technological civilization had existed long before us and practiced something like industrial agriculture, what would you look for? You'd start with a narrow slice of time where several threads come together. In marine and lake sediments from many parts of the world, you'd want to see a rapid, widespread shift in nitrogen isotopes, delta 15O, moving in unusual ways that suggest intense, large-scale disruption of the normal nitrogen cycle. Evidence for increased nutrient delivery to coasts and lakes, layers enriched in phosphorus, spikes in organic carbon, and trace metal signatures of low oxygen. Microfossil records showing abrupt algal blooms and reorganized plankton communities, not just in one basin, but across multiple otherwise unconnected systems. Crucially, you'd then have to ask, could this just be climate? Natural warming events can absolutely drive similar feedbacks. Warmer climates can increase weathering, delivering more phosphorus to the oceans. Changes in circulation can create broad oxygen pore zones. During some past ocean anoxic events, we do see exactly that pattern. Organic, rich, black shales, plankton turnovers, wild Della 15 behavior. The challenge is teasing apart the just climate cases from anything more exotic. A civilization-driven nutrient pulse would likely be unusually fast, emerging over centuries to a few millennia instead of tens or hundreds of thousands of years. It might be more tightly focused on continental margins downstream from major river systems, reflecting agriculture on land rather than purely oceanic feedbacks. It might show strong asymmetries between basins that are hard to explain with global climate alone. To really test this in deep time, scientists would need dense, high-resolution datasets. That means closely spaced sediment cores from multiple oceans and large lakes, with precise age control, detailed measurements of delta 1 total nitrogen and phosphorus in organic and inorganic fractions, surveys of microfossil assemblages across the same layers, what species appear, which vanish, how quickly, complementary proxies for oxygen levels, like trace metals and specific organic biomarkers. Stack all that together, and you'd have a nutrient cycle portrait of any candidate event, ancient or recent. Only then could you ask with a straight face whether a spike in productivity in anoxia was simply another of Earth's own mood swings, or something nudged, however briefly, by intelligent hands. And if you did find such a candidate, the next step would be to see what else was hiding in those same layers. Because nutrients and dead zones are only part of the industrial signature, The real smoking guns, if they exist at all, might lie in stranger, more stubborn traces, in the metals we smelt, the synthetic molecules we invent, and the pollutants that, unlike us, might be built to last. If you zoom into those same sediment layers and turn up the analytical resolution, you start to see something different emerging from the blur of mud and microfossils. You start to see chemistry that doesn't quite fit. One of the most obvious categories is metals. Not just any metals, specific ones, in specific patterns. Civilizations that do large-scale industry tend to concentrate certain elements far beyond their natural background. Lead in gasoline and paint, mercury in coal and gold mining, chromium and nickel in stainless steels and electroplating, copper, zinc, cadmium in batteries and electronics. We dig them out of scattered ores, run them through smelters and factories, and then inevitably leak them back into air, water, and soil. In the modern world, you can track this story layer by layer in lake muds, estuaries, and even Arctic snow. For lead, for instance, pre-industrial sediments carry very little. Then, in many cores, you see a sharp rise starting with Roman mining, a dip in the Middle Ages, and then a huge spike in the 20th century with leaded gasoline, followed by a partial decline when regulations kicked in. From Deep Time's point of view, what matters isn't the policy details. It's the shape of the signal, a geologically abrupt enrichment of multiple industrial metals, often in fixed ratios that match particular ore types or manufacturing practices, appearing more or less synchronously in sediments around the world. A past technological civilization, if it smelted ore and burned coal on anything like our scale, might leave a similar kind of metallic afterimage, thin horizons where concentrations of lead, mercury, chromium, copper, zinc, and others jump above local background by an order of magnitude or more. Those metals are stubborn. They don't decay. They can move around during burial, squeezed, dissolved, and reprecipitated. But total inventories in a given horizon tend to be conserved. 1,000,000 years of diagenesis might smear the spike, a little blur some of the fine detail, but the overall anomaly could still be detectable. And metals are only the beginning. Modern industry has also created whole families of synthetic organic molecules that don't occur in nature at all, or only at vanishingly low concentrations. Persistent organic pollutants, PCBs, certain pesticides, flame retardants, fluorinated compounds, complex halogenated aromatics. Chemists designed many of these to be hard to break down, resistant to heat, to sunlight, to biological attack. That's why they're useful. It's also why they travel. A molecule produced in one factory can volatilize, ride the wind across an ocean, condense in a cold climate, and end up in the fat of a polar bear half a world away. Some of these compounds will not survive deep burial. Complex structures get chopped up, reactive groups are stripped away. But certain motifs are remarkably tough. Chlorinated and fluorinated aromatic rings, for example, can be very resistant to degradation under anoxic conditions. Even if the original molecule doesn't make it intact, its breakdown products might. On million-year timescales, what you'd expect to see isn't a jar of pesticide waiting in the rock. You'd look for unusual distributions of specific organic fragments, strange clusters of chlorine or fluorine bound to carbon in ways that are rare or absent in purely biological compounds. You might find odd ratios of carbon chain lengths or unexpected combinations of functional groups. In other words, you'd be hunting for molecular fossils of chemistry that life left to itself doesn't usually invent. Overlying all of that is fire. Any civilization that burns fuel at scale, whether coal, oil, biomass, or something more exotic, is going to produce soot, black carbon in many forms. Tiny, inert carbon particles that can stay aloft for weeks, circle the globe, and rain out into lakes and oceans. Natural fires do this too. Every major wildfire leaves charcoal in soils and sediments. Over deep time, there are whole intervals where the rock record is peppered with charcoal and soot from vast natural burn events, especially when atmospheric oxygen was higher. So black carbon by itself isn't special. What's more diagnostic is its form and its context. Modern fossil fuel burning produces a distinctive suite of combustion residues. Among them are spheroidal carbonaceous particles, little rounded glassy bits of almost pure carbon produced when tiny droplets of fuel are heated so intensely that they partially melt and then solidify as they cool. They're a hallmark of high-temperature industrial combustion, especially coal power plants. There's also fly ash, microscopic spheres and shards of aluminosilicate glass and minerals, formed when mineral grains in coal or ash melt, and then flash freeze in rising flue gases. These particles are often enriched in certain trace elements, vanadium, nickel, some rare earths, that mirror the coal's original geochemistry. Collectively, these weird little spheres form an unmistakable fingerprint in modern sediments. Under the microscope, they jump out. Chemically, they carry a very specific story: fuel that has been ground, heated to extreme temperatures in controlled combustion, and then lofted into the air. If an earlier civilization ever burned something coal-like in large stationary furnaces, you might expect a comparable signature. A sudden appearance, in a narrow time slice, of these spheroidal particles and fly ash analogues in sediments across many continents and downwind ocean basins. Because the atmosphere and oceans are restless. Once these industrial byproducts are released, they don't stay near their source. Metals emitted from smelters or tailings ponds can attach to dust, dissolve in raindrops, and be carried across borders and oceans. Persistent organic pollutants volatilize, condense, and revolatilize in a cycle sometimes called global distillation, concentrating especially in colder regions. Soot and fly ash travel in high-altitude plumes, settling out from the Arctic to the deep sea. On a map of the modern world, that means you can find industrial fingerprints in Greenland ice, in abyssal clays thousands of kilometers from land, and in the quiet muds of remote mountain lakes. Given enough time, plate tectonics will subduct some of those deposits, erode others, and metamorphose a few beyond recognition. But some fraction will survive in stable basins long enough to be sampled by whatever curious minds come next. The difficulty, of course, is that Earth has its own ways of making confusingly similar patterns. Volcanoes, for instance, can belch out mercury, lead, arsenic, and other metals in impressive quantities. Large igneous provinces, massive episodes of basaltic volcanism, can leave behind horizons enriched in certain elements and coated with volcanic glass and ash. Hydrothermal vents along mid-ocean ridges pump metals into the deep sea, where they precipitate as metallic crusts and nodules. Wildfires and peat burns can create sooty layers with elevated black carbon. Lightning-triggered forest fires in oxygen-rich eras could, in principle, scatter charcoal across entire continents. Even some meteor impacts can generate high-temperature spherules, both silicate and metallic, that rain out globally. So if you're scanning the rock record for industrial ghosts, the job isn't just to find odd chemistry. It's to separate the weird that screams geology from the weird that hints at technology. A true industrial layer would likely show a convergence of clues: metal enrichments that don't match volcanic or hydrothermal ratios, combustion residues that look like controlled high-temperature processes rather than random wildfires, and organic molecules with structural features life doesn't normally assemble. You'd also expect a strikingly global reach on a geologically short timescale, superimposed on whatever natural background noise the planet was already making. And if you did find such a candidate horizon, mudstone or shale or silt, casually holding these little chemical riddles, the next natural question would be, what else did they make? Because metals, soot, and strange molecules are byproducts. Side effects. If a civilization is doing enough chemistry to leave those behind, it's probably also shaping matter in more deliberate macroscopic ways, which leads to one of the oddest and most revealing parts of our own Anthropocene signature. Not just invisible molecules, but tangible artifacts turned into a new kind of rock, the plastics and polymers that now carpet the planet, and whose fate in deep time is still, in many ways, an open experiment. Plastics are often talked about as if they're eternal. Bags drifting in the ocean for centuries, bottles sitting in landfills for millennia. From a human perspective, they might as well be, but from the point of view of deep time, plastics are complicated. Most modern plastics are long chains of carbon and hydrogen, sometimes with chlorine, fluorine, nitrogen, or other atoms stitched in. Polyethylene, polypropylene, PVC, PET, nylon, Teflon. Each with its own quirks, but all sharing one key trait. They weren't made by biology. They were made by us. At the surface, exposed to sunlight, oxygen, waves and abrasion, these chains start to fracture. Ultraviolet light chops them into shorter segments. Mechanical wear scuffs them into smaller and smaller pieces. A bag becomes confetti, then dust, then particles so small they look like grains of smoke frozen in place. Those tiny fragments are what we now call microplastics and nanoplastics. And they're everywhere. In beach sands, in river deltas, in deep sea mud, thousands of meters down. They get trapped in sea ice and snow, blown by the wind, carried by currents, eaten, excreted, and reburied. If you're thinking like a geologist of the future that transport is important, sediments don't just stack neatly in place, they're sorted. Fine particles tend to drift toward low-energy environments, quiet lake bottoms, continental shelves, abyssal plains. Over decades and centuries, microplastics are being swept into these same sinks, mingling with clay's organic matter and the shells of tiny plankton. In cores taken from modern oceans, you can already see this. A horizon appears where there were none before, bits of polymer mixed into the mud, increasing sharply in concentration over the last few decades. That's the beginning of the plastic layer. But what happens after thousands or millions of years? Buried under more sediment, plastics lose access to oxygen and sunlight. Temperatures rise with depth. Pressures increase. The fate of any given polymer starts to depend on its structure and its surroundings. Some chains will simply crack further, shedding small organic molecules that eventually end up as part of the general background of sedimentary organic matter. Others may partially cross-link, turning into more carbon-rich, tar-like residues. In some cases, especially under high temperatures, they can reorganize into structures not so different from kerogene, the complex mixture of organic compounds that, given more heat and pressure, can generate oil and gas. Along the way, the additives that made those plastics useful, plasticizers, stabilizers, pigments, flame retardants, metal-containing catalysts, are released or transformed. Those additives may be more chemically durable than the polymer itself. A pigment based on titanium, for instance, won't vanish just because the plastic that carried it has decomposed. So the deep time end state of a plastic layer isn't a sheet of intact bottles. It's subtler, you might find, thin horizons enriched in peculiar carbonaceous residues that don't quite look like normal organic matter, unusual concentrations of certain trace metals or organohalogen fragments, tied to pigments or stabilizers that never appear in purely biological settings, persisting shards of more resistant polymers, fluorinated chains, silicones, or cross-linked resins that hang on as tiny inert grains within the rock. These are what some researchers have started calling technofossils, not fossils of organisms, but of technology. Synthetic materials that once incorporated into sediments become part of the lithified record. Concrete with embedded plastics, asphalt reworked into conglomerates, beach sands welded with molten trash into strange hybrid rocks. People have already named plastiglomerates. On a freshly eroded cliff face millions of years from now, a future geologist might notice a thin bed where the grains aren't just quartz and feldspar, but also weird glassy beads, fragments of once flexible polymers, and carbon residues with odd isotopic or molecular fingerprints. That's the optimistic scenario for detectability. The pessimistic one is geology doing what geology does best: recycling. Most of Earth's shallow crust is not a permanent archive. Sediments are buried, heated, squeezed, and sometimes transformed beyond recognition. In regions of intense tectonic activity, whole sequences are metamorphosed. Organic matter is driven off as fluids and gases. Polymers are broken down into simpler molecules or cooked into anonymous carbon. Minerals recrystallize, erasing delicate structures. Over tens of millions of years, subduction drags oceanic crust and its sediments into the mantle. Even in stable continental interiors, erosion can plane off entire stratigraphic packages. What looks today like a global layer of plastic-laced mud could, in deep time, survive only as scattered patches in a few lucky basins that escape both uplift and subduction. And that's worth keeping in mind when we imagine earlier civilizations. We instinctively picture their plastic as ours: bags on beaches, bottles in gyres. But there's no reason to assume they followed our exact path. An earlier industrial species might have leaned much more heavily on metals, ceramics, glass, and biodegradable materials, using synthetic polymers sparingly or not at all. Or it might have developed polymer chemistry that left fewer persistent residues, materials designed to depolymerize cleanly into simple gases or easily metabolized compounds. In that case, the deep time record could hold all the hallmarks of intensive industry: metal enrichments, combustion residues, strange organics, without a single obvious plastic fragment. To a future geologist, our own technofossils may end up being just one peculiar aspect of a broader industrial signature. Useful if they survive, but not strictly necessary. Even stripped of polymers, a civilization large enough to reshape its planet would still leave traces in carbon, in nitrogen, in metals and soot. And that brings us to one of the starkest and longest lived of those traces: the fingerprints of nuclear reactions themselves, written into the isotopes of the elements. When we talk about nuclear technology as a marker of civilization, what we really mean is this: did anyone, at any time, deliberately trigger sustained chains of nuclear reactions big enough and weird enough to be written into the rocks? Because nuclear reactions don't just release energy. They shuffle the deck of the atom itself. Modern nuclear tests and reactors take heavy elements, mainly uranium-235 and plutonium-239, and split them into fragments, fission products. These fragments are isotopes of lighter elements, often radioactive, often unstable, that decay down chains toward more stable forms. You get a whole bestiary of oddities: cesium-137, strontium-90, iodine-129, technetium-99, various isotopes of plutonium, americium, curium, elements that in nature are rare or absent in those particular forms. You also get neutron activation. Otherwise, ordinary materials like iron in steel or cobalt in alloys soak up stray neutrons and become different isotopes than they started as. Even the concrete and rock around a reactor can be altered, turning stable atoms into radioactive cousins. On human timescales, these are dramatic signals. After the mid-20th century weapons tests, you can see a sharp global spike of artificial radionuclides in ice cores, lake muds and tree rings. It's so distinctive that scientists use it as a time marker, the bomb pulse. But we're not asking whether a geologist 10,000 years from now could spot us. We're asking about 10 million, or 100. On those scales, radioactive decay becomes a ruthless editor. Every isotope has a half-life, the time it takes for half the atoms in a sample to decay into something else. Many classic fission products have half-lives measured in decades. Cesium-137, about 30 years. Strontium-90, also about 30. After a few hundred years, they're mostly gone. After 1,000,000, they're effectively erased, their atoms folded back into the stable background of barium, zirconium, calcium. So what, if anything, could survive? Some isotopes decay much more slowly. Iodine-129 hangs around for about 16 million years. Technetium-99 has a half-life of over 200,000 years. Certain plutonium isotopes stretch into the tens of thousands, though even those fade on million-year horizons. Transuranic elements, those heavier than uranium, include species with long half-lives, but they tend to decay into lead, uranium or thorium, which are already common in the crust. The deep time survivable signal isn't a glowing radioactive layer. It's subtle shifts in isotope ratios of otherwise ordinary elements, lingering long after the radioactivity itself has dwindled. Imagine a mud layer on the seafloor that for a brief window of a few centuries was dusted with reactor effluents and bomb fallout. The unstable stuff decays away, but its daughters, stable isotopes of xenon, krypton, neodymium, ruthenium, are left behind in slightly odd proportions. Maybe there's a tiny excess of one xenon isotope that normally only appears in trace amounts from natural uranium decay, but here is suddenly enriched. That's the kind of thing a civilization-detecting geochemist would be hunting for. However, there's another challenge: dilution. The ocean is vast. The atmosphere even more so. Fallout from nuclear tests spread worldwide because the circulation systems of air and water are efficient at smearing signals out. That's why you can detect bomb-derived carbon-14 in organisms across the globe. But that same efficiency works against long-term preservation. A concentrated plume of isotopes becomes a globally averaged whisper. Sediments record that whisper only as a faint enrichment folded into many meters of mud. The thicker the pile, the more other stuff gets mixed in: dust from rivers, shells from plankton, volcanic ash, organic debris. Over millions of years, the original layer may be compacted, distorted, or even eroded and reworked into younger deposits. So even for our own nuclear era, the deep time question is not, will there be a glaring nuclear band in the rock record? It's, will there be a few puzzling anomalies in a handful of especially quiet, well-preserved basins? We do, however, have one crucial piece of evidence that nuclear reactions can leave an unmistakable geologic signature: the Oklo reactors in Gabon. About 2 billion years ago, in what is now West Africa, conditions in certain uranium-rich sandstone deposits were just right. Groundwater trickled through, moderating neutrons the way water does in a modern reactor. The concentration of uranium-235 in natural ore was higher then than it is today. Under these circumstances, sustained fission reactions started all by themselves. Oklo was a natural nuclear reactor. It operated intermittently for hundreds of thousands of years. And we can tell because the rocks there are weird. The uranium-235 is depleted relative to uranium-238 in patterns that match what you'd see if a reactor had been burning it. Certain fission product isotopes, especially of neodymium and ruthenium, are enriched in very specific ratios that look like the output of nuclear fuel. The surrounding minerals show evidence of neutron capture and unusual isotopic compositions. In other words, 2 billion-year-old nuclear reactions left a clear, durable isotopic scar we can still read today. That's encouraging from a Silurian hypothesis point of view. It tells us that in principle an advanced civilization's nuclear activity could show up in the deep record, not as radioactive waste drums, but as distinctive isotopic puzzles. But Oklo also shows the catch. Those signatures are only obvious because we can compare them to our understanding of nuclear physics and reactor behavior, and because the system was unusually concentrated. Lots of uranium in a confined place, running for a long time. To distinguish natural from technological nuclear signatures, you'd be looking for combinations that nature doesn't usually produce. Natural reactors like Oklo require specific geological conditions and tend to be localized. Their fission products mostly stay put. A technological civilization, by contrast, might scatter isotopes around the globe in patterns tied to industrial centers, prevailing winds or ocean currents. You might see enrichments of elements, like technetium and certain plutonium isotopes, in environments where uranium concentrations are otherwise low, or odd activation products in steels and concretes that got eroded and redeposited as sediment grains. You'd also look for timing. Natural nuclear phenomena are ancient and rare. A sudden global appearance of unusual isotope ratios, coincident with other markers, carbon shifts, metal spikes, synthetic organics, would be harder to explain as purely geologic. So far, we haven't found anything like a global Oklo plus industry layer in older rocks. No billion-year-old band with technetium anomalies tied neatly to a carbon isotope spike and a burst of pollution metals. Our own nuclear footprint, only a few decades old, is just beginning to be buried. In that sense, the absence of deep-time nuclear oddities is suggestive. It makes a prior large-scale fission using civilization less likely, at least one that looked technologically similar to us. But it's not a final verdict. A civilization that used little or no fission, or that confined its nuclear activity to small, geologically unlucky regions that have since been subducted, eroded, or metamorphosed, might leave almost no detectable nuclear trace. One that preferred fusion or energy sources we haven't imagined yet might not leave a nuclear signature at all. So nuclear scars are a powerful test, but not a definitive one. They're one line of evidence among many, and if we want to think like detectives of vanished civilizations, our next step is obvious. Ask where the most fragile and exotic of these clues would actually stand a chance of surviving. Where, on a restless planet, would you hide evidence and hope it lasted hundreds of millions of years? If you're hunting for ghosts in the geologic record, the first thing to understand is this. Most of Earth's surface is a write and erase board, not a bookshelf. Let's start with the oceans, because that's where most of our industrial junk is actually ending up. It's tempting to imagine some future geologist dropping a drill into the Pacific and hitting a neat little layer labelled Anthropocene, like a bookmark in the seafloor. But the ocean crust under that mud is young, shockingly young. New seafloor is born at mid-ocean ridges, where molten rock wells up and freezes, pushing older crust sideways like a conveyor belt. At the other end of the belt, in subduction zones, that crust dives back into the mantle and melts. On average, this whole cycle takes about 150 to 200 million years. That sounds like a long time. But remember, the Earth is over 4.5 billion years old. That means, essentially, none of the seafloor is older than the age of the dinosaurs. Go back to the Silurian period, 430 million years ago, and the entire global ocean floor from that time is gone. Recycled, cooked, erased. So if your hypothetical pre-human civilization was mostly coastal and marine, and it lived hundreds of millions of years ago, much of its physical footprint would literally have been dragged underground and melted. That doesn't mean oceans are useless as archives. The mud on top of that moving crust can be older than the basalt beneath, especially in the very slow-spreading quiet parts of the deep sea. Some of those deep-sea sediment piles are tens of millions of years thick. That's where ocean drilling programs go to reconstruct climates, extinctions, and chemical changes. If you wanted to look for long-lived chemical fingerprints, odd isotope ratios, strange metals, weird organic residues, those old deep-sea muds would be on the target list. Not the flashy mid-ocean ridges, but the calm abyssal plains far from plate boundaries, where sediments fall like dust and nothing much disturbs them. Still, the best long-term archives are usually on land, in places where water has quietly laid down layer after layer of sediment, and then walked away. Continental sedimentary basins are prime, ancient lake beds, inland seas, river deltas that slowly piled up silt and clay for tens of millions of years. The interiors of big continents often host these basins, thick stacks of mudstone, sandstone, limestone, each layer a page. If a civilization altered the atmosphere, fertilized the land, spiked the rivers with metals, those basins are where the chemical record is most likely to accumulate and stay put. Lakes, especially deep, stable ones, are even better short to medium-term diaries. Year after year, they lay down couplets of light and dark layers, summer and winter, that can preserve pollen, ash, organic molecules, and delicate chemical patterns. On million-year scales, many lakes come and go, but some persist long enough to catch major transitions. What about polar ice? Modern climate science leans heavily on ice cores from Greenland and Antarctica, pulling bubbles of air out of cylinders of ice to read past atmospheres. For our own industrial age, ice is an incredible record. It shows carbon dioxide increases, lead pollution, even the radioactive bomb spike. But ice is fragile on deep time scales. Ice sheets flow, they deform, melt from below, break off as icebergs. The oldest continuous Antarctic ice may be around 1.5 million years. There are hints of older buried ice in special settings, but we're nowhere near tens of millions of years, let alone hundreds. For a Silurian age civilization, there would simply be no ice left to read. Rock, not ice, has to carry that story. Some rocks are unusually friendly to preservation. Caves, for example, in limestone regions. Water carves out underground chambers where sediments, bones, and chemical deposits can accumulate in protected darkness. Stalagmites can record changes in rainfall and temperature in their growth bands, like mineral tree rings. A cave system that stays above sea level for a long time can quietly store a very local but very detailed archive. Amber is another time capsule. Sticky tree resin traps insects, pollen, sometimes tiny fragments of the world outside, then hardens and is buried. Amber doesn't last forever, but it can persist for tens of millions of years. It's no good for cities or machines, but for microtraces, pollens, spores, maybe industrial soot particles, it's a surprisingly resilient medium. Evaporites, thick layers of salt and gypsum left behind, when seas or lakes repeatedly dry out, can lock in dissolved ions and tiny inclusions of ancient fluids. They form in hot, arid basins where water keeps evaporating faster than it arrives. Once buried, they can be very stable, and the brines trapped within them can preserve the chemical flavour of ancient waters with uncanny fidelity. Then there are anoxic basins, places where the bottom waters of a lake or sea are so depleted of oxygen that almost nothing can live there, and crucially, nothing can stir the mud. In those silent depths, thin laminae of sediment stack up like the pages of a book, unbioturbated, undisturbed. Black shales, the dark, organic, rich rocks that often form from such settings, are among the best long-term records of past chemistry. If an industrial civilization ever triggered a burst of ocean dead zones, these are the rocks most likely to whisper about it. To reach many of these archives, you can't just walk up to an outcrop and tap it with a hammer. You have to drill. Drill cores are time machines. A cylinder of rock pulled from a kilometre underground preserves the original order of layers that might never be exposed at the surface. Oil companies, groundwater surveys, scientific deep drilling projects, all of them pull up archives that cross boundaries in time no natural cliff ever shows. For Silurian Hypothesis detectives, the subsurface is essential. Much of Earth's best preserved record never makes it to daylight. It's buried, compacted, and quietly waiting in the dark. And this leads to the last uncomfortable point: sampling bias. When you look at a geologic map, the coloured patches of rock give the impression that we've seen everything. In reality, we've examined a tiny fraction of Earth's crust at high resolution, and only in convenient places, along roads, in mines, in a handful of drill sites, in countries that fund geology. Most of the deep ocean floor has never been cored. Huge stretches of continental interiors are covered by soil and vegetation. They're deeper rocks known only from a few scattered boreholes. Even where outcrops are accessible, only a sliver of them have been sampled for exotic isotope ratios or mysterious organic molecules. From a Silurian perspective, that means two things can be true at once. So far, we haven't seen any convincing trace of a pre-human industrial civilization in the places we've looked. And yet, most of the planet's potential hiding spots, quiet basins, buried lakes, deep black shales, remain essentially unread. If you wanted to hide evidence for 400 million years, you wouldn't put it on a mountaintop. You'd drop it into the kinds of archives we've just described, then trust plate tectonics and erosion to do their slow, selective editing. But even if a civilization did that, there's another harsh reality to face. The artifacts themselves, the buildings, the machines, the roads are almost certainly gone. What survives best over deep time isn't architecture. It's chemistry. To understand why, we have to look at cities the way a geologist does, not as skylines, but as future sediments. From a human point of view, cities feel enormous and permanent. Concrete canyons, steel skeletons, highways thick as scars. We compare them to pyramids and castles and call them everlasting. From a geologic point of view, they're just oddly flavoured dust. Take a modern city. Strip away the lights and motion, and you're left with piles of processed rock and metal sitting on the thinnest skin of the planet. That skin is constantly being chewed, cracked, soaked, and rearranged. Rain infiltrates concrete, rust eats steel, frost shatters foundations. In humid climates, vegetation starts the demolition almost immediately. Roofs collapse. Slabs fracture, rebar expands and bursts its mineral shell. Within a few thousand years of abandonment, many structures would be reduced to rubble mounds. Then erosion takes over. Water is the main architect of Earth's surface. It cuts, sorts and carries. Rivers chew into old floodplains. Storms undercut cliffs. Landslides sweep away entire hillsides. Very quickly, in geologic terms, the neat geometry of buildings is broken, tumbled, and mixed into ordinary sediment. Give it a few million years and you're not looking at a city anymore. You're looking at a layer of sandstone or conglomerate, with a slightly odd mix of grains. Some glass shards here, some corroded metal oxides there, maybe a few stubborn bits of ceramic. To a field geologist, it reads as anthropogenic debris, if it's recent. Stretch the timeline to tens of millions of years, and those clues get thinner, smaller, harder to distinguish from natural lookalikes. Now add burial and tectonics. Most of the land surface is slowly subsiding or being uplifted. Where it subsides, sediments pile up. Any old urban layer that gets buried under hundreds or thousands of meters of mud and sand is eventually compacted, cemented, heated. Minerals recrystallize. Porous spaces collapse, fine details vanish. Where continents collide or stretch, rocks are bent, faulted, sometimes metamorphosed. Their original structures are smeared out, tilted, overturned. After a full tectonic cycle or two, what used to be a coastal plain with cities might be a belt of folded mountains with no obvious trace of its former surface. And that coastal plain part is crucial, because humans, like many intelligent hypothetical species, are strongly coastal. Coasts are where rivers deliver nutrients, where trade routes are short, where climates are often gentler. Today, a huge fraction of humanity lives within a narrow band of sea level. If a civilization before us followed a similar pattern, most of its major settlements would have hugged shorelines. But shorelines move over millions of years. Sea level has swung up and down by hundreds of meters. Coasts flood, retreat, drown under deltas, or are planed off by waves. Add in that many coasts sit near active plate margins, subduction zones, rift systems, transform faults, and you have the worst possible place to store delicate ruins. They're either eroded, buried in unstable sediments, or eventually dragged down a trench and melted. So what, if anything, architectural might actually endure? Deeply buried foundations sometimes fare better than what sits on top of them, especially if they're cut into hard rock. Subsurface infrastructure, tunnels, deep basements, subway systems could be more resistant to surface weathering, at least for a while. Over long spans they would still fill, compact and deform, but fragments of their geometry might survive as unusual voids or cemented horizons. More likely than clean structures are mineral oddities, zones of strange glassy materials from high-temperature processes, layers rich in brick fragments and ceramics, horizons where the normal progression of soil minerals is interrupted by manufactured compounds. These become part of the rock record as unusual mineral assemblages, rather than recognizable objects. Mining is another candidate for long-lived marks. Large open-pit mines excavate entire hillsides, leaving amphitheatre-shaped scars with walls of exposed rock. Underground mines honeycomb regions with tunnels and stopes. Around both you get enormous piles of waste rock and tailings, finely ground material chemically processed to remove valuable metals. Over time, pits can fill with sediment or water and blend into the landscape. Tailings can be eroded and redistributed, but the combination of emptied ore bodies, weirdly altered rock chemistry, and peculiar sediment geometry can persist. Even when the physical pit is gone, a geologist might still find an ore deposit that is inexplicably depleted in high-grade material, surrounded by halos of chemical alteration that don't match any known natural process. At our own current level of technology, we already leave these signatures. Bauxite stripped from tropical soils, copper and rare earths torn from specific veins, entire coal basins partly emptied. Scale that up to a truly industrial civilization lasting millions of years, and the pattern of missing ore, plus odd tailings trapped in basins, could be one of the clearer clues that someone had been digging before us. Still, notice the pattern here. None of this looks like a lost Manhattan sitting intact in the rock. It looks like subtle distortions, depleted seams, strange glasses, chemically quirky layers. Things you have to sample, measure and interpret, not photograph. That's why, though, we haven't found any ancient city's argument doesn't carry much weight at multi-million-year timescales. We wouldn't expect to. The probability of a skyscraper, or even a recognizable building, surviving intact for tens of millions of years is effectively zero. The chance that we've carefully sampled and analysed the exact cubic kilometre where its powdered remains ended up is also tiny. Which brings us back to chemistry. A civilization big enough to mine continents and build global cities is a civilization big enough to perturb the carbon cycle, the nitrogen cycle, the metal budget of the oceans, perhaps even the isotopic makeup of the atmosphere. Those signals don't rely on a single site or a fragile ruin. They spread planet-wide, get written into deep-sea muds and continental basins in countless independent copies. Artifacts are local and fragile. Global chemical markers are redundant and stubborn. If we're going to look seriously for the deep time echo of a non-human civilization, we're not really hunting for buried skyscrapers. We're hunting for sudden, unnatural changes in the chemistry of rocks. And that's exactly what the Silurian Hypothesis zeroes in on next. The obvious next question is, has Earth ever done something like this before? Has the planet's chemistry ever lurched in a way that, if we didn't know better, might make us whisper, "That looks suspiciously industrial"? There's one episode that keeps coming up in these conversations. It has a long, clumsy name, but it's worth learning. The Paleocene-Eocene Thermal Maximum. Most people just call it the PETM. Roll the clock back about 56 million years. No humans, no apes, no ice caps. The world is already warm, a greenhouse planet with crocodiles in what is now the Arctic. Then, on top of that, something happens. In geologic terms, it happens fast. Temperatures jump by about 5 to 8 degrees Celsius globally. That's the kind of warming climate models predict for an extreme, runaway version of our own future. But the PETM did it from an already hot starting point. In the rock record, this shows up as a sharp carbon isotope excursion. Layers of sediment from that time suddenly have far more carbon-12 compared to carbon-13 than the layers above and below. That ratio shift tells you a story. A huge pulse of light carbon hit the atmosphere-ocean system. At the same time, the oceans acidified. Tiny marine organisms that build shells from calcium carbonate show signs of dissolution. Deep-sea sediments lose their carbonate content entirely for a while. It's like someone turned up the acidity knob on the global ocean and started dissolving chalk from the bottom up. Warmer air, sour oceans, a big isotopic lurch. On a graph, the PETM looks unnervingly like a supersized, stretched-out version of the industrial carbon spike we're currently generating. That's why some researchers have called it a natural experiment in rapid carbon release. If we want to know what the long-term geological record of a carbon-burning civilization might look like, the PETM is one of the closest natural analogues we have. It resembles an industrial carbon pulse in some important ways. There's the speed. For deep time, this is abrupt. Estimates put the main carbon release over perhaps 5,000 to 20,000 years, maybe with faster bursts inside that window. Not a single volcanic eruption that comes and goes in a decade, not a slow drift over millions of years, but a geologically sharp jab. There's the magnitude, thousands of gigatons of carbon added to the system, enough to rewrite global climate, reorganize ecosystems, and leave a clear chemical scar in sediments worldwide. But there are also key differences, and they matter if we're trying to use the PETM as a test case for hidden civilizations. First, timescale. Even at its fastest credible pace, the PETM carbon release is still much slower than what humans are doing right now. We are cramming a PETM-level dose of carbon into the atmosphere in centuries, not millennia. That difference in rate is something geochemists pay close attention to. The steeper the curve, the more suspicious it looks. Second, carbon sources. Everything we know about the PETM points toward natural reservoirs. Possibilities include massive volcanic intrusions, baking organic rich sediments, destabilization of methane hydrates on the seafloor, or oxidation of peat and shallow coal. Each of those has a characteristic isotopic flavor, and models suggest you need a mix of them to get the PETM pattern. There's no clear sign of the very specific isotopic and molecular cocktail you'd expect from burning deeply buried, selectively mined fossil fuels with modern-style industrial efficiency. Instead, you see something messier, more diffuse, more in line with big natural perturbations. Third, sedimentary context. The PETM sits inside a world that already makes sense without invoking technology. You have gradual background warming driven by long-term tectonics and orbital changes. Then this sharp event. Then a slow recovery as Earth's weathering feedbacks pull carbon back out of the air and lock it into rocks again. Around the PETM, you don't find layers of exotic industrial byproducts. No spikes of synthetic metals, no odd polymers, no pan-continental horizons rich in strange glass or artificial alloys. You do find biological responses, dwarfing of some mammal lineages, migrations of plants and animals, changes in marine plankton communities. It looks like a biosphere reacting to climate stress, not a biosphere plus a technosphere collapsing together. So, when scientists study the PETM with the Silurian hypothesis in mind, they're not just asking, was there a civilization? They're asking a more constrained question. If there had been one, would anything in this event force us to take that seriously? They look at the rate of carbon release. They compare carbon isotope patterns to what we'd expect from our own fossil fuel binge. They scan for accompanying markers, unusual metal distributions, weird nitrogen and phosphorus signatures, compound classes that don't show up in purely natural systems. So far, nothing at the PETM screams artificial. It looks, as far as we can tell, like a particularly wild swing of the natural carbon cycle. A big burp, not a factory exhaust. But here's where the ambiguity creeps back in. 56 million years is a long time. The resolution of our record blurs as you look that far into the past. A technological species that flared and vanished over, say, 50,000 years, 10 times longer than our industrial age, but still a blink to geology might have its sharpest signals smeared out in the muds and limestones we see today. From our current sampling, from the cores we've drilled and the outcrops we've walked, the PETM doesn't need a civilization to explain it. Natural processes fit the data just fine. But can we absolutely mathematically rule out any technological contribution? Not really. The record isn't that precise, and our coverage isn't that complete. What the PETM really teaches in the context of the Silurian hypothesis is less about hidden empires and more about detectability. It shows that Earth can, on its own, produce events that mimic some of the geochemical fingerprints we're tempted to call industrial. It reminds us that even large, rapid disturbances can end up looking smooth and rounded in the rock record. And it warns us that when we comb deep time for anomalies, we're going to run into natural false positives, events that look strange, even alarming, but are still entirely the work of plate tectonics, volcanism, and the restless carbon cycle. If we want to sharpen our search, we have to set the PETM on the table, examine it carefully, and then ask, are there other events that go even further? Episodes where the carbon spike is paired with something else, something harder to fake with mere geology. And that's where we turn next. The PETM isn't the only time Earth seems to have slammed its own red panic button. If you zoom out and look across the last few 100 million years, you start to see other sharp breaks in the record. Some show up as sudden warmth, some as sudden die-offs, some as eerie chemical fingerprints written into ocean mud. To someone hunting for ancient industry, these are the confusing ones. The wait that looks weird moments. One major category has an ominous name, Ocean anoxic events. Anoxia just means no oxygen. During these episodes, huge parts of the world's oceans basically suffocated. Surface waters might still hold life, but deeper layers turned into stagnant, dark brine where almost nothing complex could survive. In the rocks, anoxic events leave a very particular calling card. You get thick layers of black shale, fine-grained mud, rich in organic matter laid down in quiet, oxygen-poor water. Because there's no oxygen, dead plankton and other debris don't fully rot. They pile up and get buried almost intact. Those black shales often show strong shifts in carbon isotopes, just like the PETM but with added twists. You see unusual ratios of sulfur isotopes, indicating that sulfate-breathing microbes took over where oxygen-breathing life failed. You see enrichments of certain trace metals like molybdenum, uranium and vanadium that get concentrated when seawater goes low oxygen. Sometimes the anoxia isn't just local, it spreads across entire ocean basins. That's when geologists start talking about oceanic anoxic events with capital letters, OAE1, OAE2 and so on, especially in the mid-Cretaceous around 90 to 120 million years ago. What drives something that extreme? Very often those black shales line up in time with another geological suspect, large igneous provinces. A large igneous province is what you get when the planet decides that a regular volcanic eruption is too subtle. Instead of one volcano, you open up enormous fissures or even whole regions and flood them with lava over relatively short geological times. The Siberian Traps, the Deccan Traps, the Central Atlantic Magmatic Province. These are not gentle events. They are planetary-scale outgassings. When those provinces erupt, they don't just pour basalt onto the surface. They release staggering amounts of carbon dioxide and other gases. They can inject aerosols into the atmosphere, warm the climate, acidify the oceans, and scramble weather patterns worldwide. In the sediment record, you often see the sequence. First, signs of intense volcanism. Ash layers, strange magnetic signatures in the rocks. Basalt provinces dated to that window. Then a greenhouse spike, warming changes in carbon isotopes. Then, as the system responds, widespread anoxia in the oceans, black shales, metal anomalies. The biosphere, pushed to the edge, starts to break. Sometimes it breaks hard enough that we call it a mass extinction. Think of the end Permian event, about 252 million years ago, when an estimated 80 to 90% of marine species vanished, or the end Triassic, or certain Cretaceous crises. Many of these line up with large igneous provinces and with rapid climate and ocean chemistry changes. From the perspective of the Silurian Hypothesis, that combination, rapid warming, disrupted nutrient cycles, collapsing ecosystems, starts to look uncomfortably like an industrial civilization wrecking its own world. Rapid extinction can even mimic what we might call anthropogenic patterning. You see certain groups hit harder than others. Food webs reorganize, opportunistic species take over disturbed environments. On land, fires become more common as climates shift. In the sea, algal blooms and dead zones proliferate. If you were just handed those patterns without context, you might be tempted to ask, was somebody burning fuel, fertilizing oceans and dumping waste? This is where timing and multi-proxy correlation become crucial. Geologists don't just look at one line on a graph. They cross-check many different kinds of evidence. Carbon isotopes, yes, but also sulfur, nitrogen and strontium. Metal concentrations, rock types, fossils, paleomagnetic reversals used for dating, radiometric clocks in volcanic minerals. For many mass extinctions and anoxic events, the story that emerges is internally consistent without invoking technology. You can correlate the onset of volcanism, the rise of CO2, the warming, the spread of anoxia, and the biological crash. Different proxies from different places on Earth all point to the same sequence of natural triggers and responses. So if we want to avoid being fooled by natural false positives, we need a checklist, an internal standard, for what would really count as a technosignature in deep time. It would have to be something more than rapid warming, carbon isotope excursion, anoxia and extinctions. Earth can do all of that by itself. A technosignature in this context would need extra layers. You'd look for combinations that are very hard to produce with volcanism and normal biogeochemistry alone. For example, a sharp, globally synchronous rise in certain metals that are usually associated with ore refinement, unusual distributions of platinum group elements, rare earths, or very pure aluminum that doesn't occur naturally in that form. You'd look for persistent organic pollutants, complex synthetic molecules with distinctive structures that don't match known biological or volcanic compounds. You'd expect weird nitrogen and phosphorus signatures consistent with industrial-scale fertilizer use, not just natural nutrient runoff. Maybe even isotopic ratios in those nutrients that show they've been processed and concentrated, not simply weathered out of rocks. You might see changes in sediment grain sizes and sources around ancient coastlines that suggest engineered land use. Massive, sudden increases in erosion from deforested landscapes, paired with strange coastal subsidence patterns more in line with megacities than with normal river deltas. And critically, you'd want those anomalies to line up in time, globally, in a way that's hard to explain by one big volcanic province or one asteroid impact. Not just one basin, not one ocean, but many independent records, all whispering the same odd story. The more of those boxes you can tick at once, the harder it becomes to wave everything away as just another wild natural swing. So when scientists look at ocean anoxic events and mass extinctions with the Silurian Hypothesis in mind, they're effectively running that checklist. Most of the time, the verdict is clear. Spectacular, frightening, but natural. But the exercise is useful because it sharpens our sense of what to look for if we ever do stumble across something that doesn't fit the usual patterns. And it sets us up to ask a more specific question about the namesake of the hypothesis itself. If you go back not tens of millions of years, but hundreds, back into the real Silurian period, what kind of world are we actually dealing with? And would it even be a plausible cradle for a technological experiment? To answer that, we need to leave the familiar world behind almost completely. The actual Silurian period runs from about 443 to 419 million years ago. That's not just before dinosaurs. That's before forests, before insects with wings, before anything with a backbone had really committed to living on land full-time. If you could stand on a Silurian shoreline, the first thing that would hit you is how wrong the continents look. Most of the landmass is gathered into a few strange configurations. There's Gondwana, a supercontinent sprawled across the southern hemisphere, dipping down toward the South Pole. There are smaller continental blocks, Laurentia, Baltica, Siberia, drifting in the tropics and subtropics. Islands and mini-continents rather than the big familiar shapes we know today. Sea level is high, shallow epicontinental seas, broad, warm, relatively shallow waters flood huge swaths of those continents. Much of what counts as land is really just low-lying coastal platforms, tidal flats, lagoons, reef-rimmed basins. Dry, high interior continents the size of Asia are not really a thing yet. The climate backdrop is surprisingly gentle. The Silurian opens just after a major glaciation and mass extinction at the end of the Ordovician. Ice sheets begin to retreat. Over the period, the world trends toward a greenhouse state. Warmer oceans, less polar ice, more humid low latitudes. Not stable in a modern day-to-day sense, but broadly mild by deep time standards. Life, however, is still mostly in the water. Silurian seas are busy, layered ecosystems. Coral-like organisms and stromatoporoids build reefs that can run for hundreds of kilometers. Jawless fish armored with bony plates cruise above the seafloor. The first true-jawed vertebrates are appearing, small experimental versions of the fish line that will eventually give rise to sharks and, much later, to us. Trilobites are still around, though past their peak. Eurypterids, sea scorpions, prowl the shallows, some of them reaching over 2 meters long. Early nautiloid cephalopods drift and hunt. The plankton are different too. Graptolites and a cast of extinct microfossils dominate the open water. On land there is life, but it's nothing like a forested world. The earliest vascular plants have just started to colonize damp shorelines and river margins. Think low mats, simple stems, maybe knee-high at most. No true leaves, no flowers, no seeds. Spores do the work that seeds will do much later. Terrestrial ecosystems are basically microbial crusts, algae, lichens, and very simple plants clinging to wet ground. There are probably early arthropods venturing out, primitive millipede-like or spider-like creatures, but terrestrial food webs are tiny and local. There are no towering trees, no deep soils rich with roots and worms, no thick peat bogs stretching to the horizon. That matters for the Silurian hypothesis in a very specific way. Our own industrial civilization is tied to enormous ancient reserves of concentrated energy, coal, oil, gas. Most of the world's coal comes from later periods, especially the Carboniferous and Permian, when vast swamp forests laid down thick beds of peat that were buried, cooked, and turned into coal seams tens of meters thick. In the Silurian, that system hasn't been built yet. There simply aren't the dense, large, woody plants needed to create massive coal deposits. Organic matter is being produced, of course, and buried in marine shales and in small peat, like accumulations on land. But the global landscape isn't generating the kind of huge, laterally extensive carbon reservoirs we dig into today. That doesn't make energy impossible. It just means any hypothetical civilization would be working with a very different resource base. No convenient Carboniferous coalfields, no Mesozoic oil basins full of dinosaur-era plankton. At best, more scattered, thinner, organic, rich sediments. Perhaps more dependence on direct solar, on wind over shallow seas, on geothermal, on whatever clever tricks evolution might provide. And that leads to a subtle point that often gets lost when people first hear Silurian Hypothesis. The name is a joke. It comes from Doctor Who, specifically the Silurians, a race of intelligent reptilian beings who supposedly evolved on Earth long before humans and then went into hiding. When the actual scientists, Adam Frank and Gavin Schmidt, wrote about the idea, they borrowed that name with a wink. They weren't claiming that there really was a civilization in the literal Silurian period. They were asking a broader question. If some industrial civilization had arisen at any point in deep time, how would we recognize it now? Still, using the Silurian as a thought experiment is useful because it's such an alien world. To get industrial technology going there, a species would have to overcome multiple stacked challenges. They'd need to make the leap onto land, or at least into the very shallow coastal zone, without the ready-made support of complex oxygen-rich forests and deep, stable soils. They'd have to develop metallurgy in a world where easily accessible oxidized metal ores might look very different, and where fire-based technology is confined to sparse, low vegetation and dried microbial mats instead of big forests. They'd need ways to concentrate energy and materials when the biosphere isn't yet great at stockpiling them. That could mean far more reliance on chemistry we don't typically think about, harvesting energy from redox gradients in coastal sediments, or from hydrothermal systems, or even from biological partners engineered or evolved to do that work. In other words, a Silurian-era civilization, if it somehow appeared, would almost certainly not be a mirror of ours. It would be solving the problem of technology under a completely different set of constraints, and if it had existed, the traces it left behind would now be buried not just under one cycle of mountain building and erosion, but under 500 million years of shifting oceans, colliding continents, and metamorphic overprint. Which brings us to the next problem. Given those conditions, could any technosignature from that far back survive at all, and if so, what would it even look like? To even ask that question, we have to separate a few things that our own history tends to blur together. Intelligence is one thing, culture is another, industrial civilization is something else again. Plenty of animals alive today are clearly intelligent by any reasonable standard. Octopuses can solve puzzles, open jars, recognize individual humans. Crows and parrots use tools, plan ahead, understand simple cause and effect. Whales and dolphins have complex social lives, regional dialects, even what looks suspiciously like traditions. That's intelligence and culture, but none of them are smelting copper or launching satellites. Industrial capability seems to require a very specific bundle of traits coming together at the same time. The first is physical. To build machines the way we do, you need manipulators that are both strong and precise. Hands with opposable thumbs are one solution. Tentacles, trunks, or prehensile tails might work too. What matters is the ability to grasp, rotate, pinch, and apply controlled force to small objects. You also need reliable control of fire, or at least of high temperatures. Metallurgy is basically the art of persuading rocks to melt, separate, and re-solidify in useful ways. Without the ability to sustain combustion, control airflow, and hold materials in hot, confined spaces, you never leave the Stone Age. Then there's social learning. One individual solving a problem is nice. A population that can copy, refine, and transmit that solution across generations is civilization in embryo. That means long childhoods, time for teaching, brains wired not just to invent, but to imitate and standardize. Lifespan matters too. If most adults die before they're 30, the chain of apprenticeship is fragile. Longer lives allow a single inventor or master craftsperson to train multiple cohorts to accumulate, test, and revise techniques over decades. So when we imagine a hypothetical Silurian-era technologist, we're really asking, could any lineage back then have converged on something like nimble manipulators, fire control, social transmission of skills, and reasonably long lives? Maybe. But the physical prerequisites are only half the story. There are ecological constraints as well. Technology, especially early industrial technology, is hungry. It eats energy and raw materials. To sustain that, you need surplus, food beyond what daily survival demands, energy sources beyond body heat and muscle power. That usually means relatively stable environments. Floodplains that don't shift course every decade, coasts that aren't constantly drowning or drying out, climate swings that are slow enough for agriculture, like strategies to pay off. You also need easy access to useful stuff, exposed metal ores, workable stone, clay, fuels. Our own civilization was bootstrapped on places where copper literally stuck out of hillsides, where rivers cut through iron-rich layers, where forests or peat or later coal could be harvested in bulk. Now imagine trying to do all that in the ocean. Marine life solves its problems chemically and behaviorally, not with fire and furnaces. Underwater, open flames are impossible. Combustion engines don't work. Even simple things like baking clay into ceramic, are suddenly non-trivial tasks. Metallurgy under salt water is especially difficult. You have to reach high temperatures in a medium that sucks heat away, with oxygen and corrosive salts all around. It's not impossible in principle. An aquatic species might use enclosed air pockets, geothermal vents, or even biology to concentrate heat, but it's a much steeper climb than rubbing sticks together on dry land. And yet the ocean is where complex life got its start. In the Silurian, it's where almost all the action is. If any non-human intelligence had the time and ecological space to get weird, it would probably be there. So some researchers play with alternative paths. What if a lineage leaned hard into biotech instead of metallurgy? Imagine a civilization that never discovers steel, but learns to domesticate and re-engineer other organisms. Structures grown from directed coral, tools and containers secreted by symbiotic shell builders, light provided not by burning fuel but by cultivated bioluminescent bacteria, or a chemistry-driven culture. Instead of engines, they build pumps and pressure systems. Instead of circuits, they use reaction networks, exploiting pH gradients and controlled crystallization as their information technology. Their factories might look to us like elaborate reefs or mats, quietly rearranging elements instead of belching smoke. Those paths are speculative, but they make a key point. Industrial-scale influence on a planet doesn't necessarily mean smokestacks and blast furnaces. It means large, coordinated flows of energy and materials, no matter how they're achieved. So when we talk about non-human intelligence and ancient technology, we have to walk a narrow line. We can say there's no evidence of anything like that in the Silurian, or any other deep time window we've studied so far. We can say that, given what we know about physics, chemistry and evolution, land-based tool users with some form of fire control are the easiest route to an industrial footprint like ours. But easiest is not the same as only. The Silurian hypothesis isn't claiming secret lizard empires or hidden octopus cities. It's asking us to think carefully about which evolutionary and ecological combinations are actually capable of reshaping a planet and what signatures they would leave behind. Once we have those constraints in mind, we can turn to the most practical question of all. If something like that ever did happen on Earth or anywhere else, where should we be looking for the faintest surviving traces? If you're looking for traces, one thought comes up almost immediately. Stop staring only at Earth. Our planet is a master of self-erasure. Weather, water, biology, and plate tectonics are constantly grinding, burying, and recycling the surface. Give Earth a few 100 million years and it turns continents into soup, then rock, then new continents. Archaeology is trying to read a book that keeps shredding and rewriting its own pages. But not every world is like this. Think about the moon. No air, no rain, no rivers, no forests, no plate tectonics. Its crust doesn't get chewed up and pushed down into a mantle conveyor belt. It just sits there, on an airless body like the moon. There's nothing to round off sharp edges except sunlight, temperature swings, and tiny impacts. A footprint from Apollo is expected to last for millions of years. The glassy beads formed by an impact billions of years ago can still lie almost where they fell. The surface, in geological terms, is almost pure memory. That's why some people have suggested that if a past industrial civilization ever reached space, the moon would be one of the best archives of its existence. What might we look for at the simple end? Artifacts. Leftover hardware, structures, unnatural pits or trenches, a long, straight tunnel into bedrock, a regular grid of holes. Anything that screams tool use rather than random geology. Then there are mining scars. A spacefaring species might not need to build big cities on the moon, but it has a lot of incentive to dig. Metals, helium-3, rare elements locked into ancient basalt. Mining on a body with almost no weather means that the scars could last an absurdly long time. Stripped craters, clean-edged pits with steep walls, tailings piles poured where no impact or volcanic process would leave them. At a more subtle level, there are chemical and isotopic traces. Industrial activity reshuffles isotopes in distinctive ways. You enrich some, deplete others, leave behind alloys and compounds that don't occur naturally. A civilization doing large-scale processing of lunar rock might create weird pockets in the regolith, unusual mixtures of metals, odd ratios of stable isotopes, synthetic compounds that, like some of our fluorinated chemicals, simply don't participate in ordinary geochemistry. So does that mean the Moon is a pristine, eternal time capsule? Not quite. Even without air or water, there is still weather of a sort, micrometeorites. For billions of years the Moon has been sandblasted by dust and gravel. Every impact, even tiny ones, break rocks apart and mix them downward. Over time, this impact gardening churns the upper layer of soil. A sharp-edged footprint slowly gets blurred as grains hop in and out. A metal fragment gets buried, then exhumed, then buried deeper. A large crater can obliterate everything for hundreds of kilometers. Lava flows in the Moon's distant past, resurfaced whole regions. So while many traces can last a long time, nothing on a planetary surface is truly eternal. We also have a very incomplete map. Humans have walked on 6 landing sites. Robotic landers and rovers have sampled a handful more. Orbiters have imaged the surface at high resolution, but high is relative. You can pick out the descent stages of Apollo, sure, but a collapsed mine shaft 10 meters wide, a small field of strange rubble, that's much harder. Vast areas have been surveyed only coarsely. If you wanted to hide an ancient lunar quarry, you'd have tens of millions of square kilometers to choose from. Mars sits in an interesting middle ground. It's not airless. It has wind, dust storms, frost, even in its early history, water flowing across the surface. Its rocks erode, dunes migrate, valleys deepen, but Mars has no plate tectonics as far as we can tell. Its crust doesn't seem to get constantly recycled into the interior the way Earth's does. That makes Mars more like a stratified archive. Layers laid down billions of years ago can still sit at or near the surface today. Ancient lake beds, river deltas, volcanic plains, all frozen in place. Erosion carves into them, but doesn't consume them completely. For technosignatures, that matters. If any civilization, Martian or visiting, ever altered a region on scales large enough, some imprint might still be accessible. Unnatural layering in sediments, anomalous metal concentrations in old lake deposits, odd geometries half buried under dust. Even if structures themselves crumbled, the debris field and the geochemical halo could linger. Modern missions are, in principle, capable of noticing a few of these things. Orbiters already detect mineral compositions from space. They can flag patches of rock that look chemically strange. Rovers can grind into stones, analyze elemental makeup, even probe isotope ratios for some elements. If you parked a rover next to a rusted-out alien refinery, it would know something unusual was going on. The catch is coverage. We've landed in a handful of safe, relatively flat regions. We're not sampling randomly. We're following water, sedimentary history, scientific priorities. The odds that we've trundled directly over a million-year-old industrial site, if one even existed, are vanishingly small. So looking to the Moon and Mars doesn't replace the deep detective work we do on Earth. It complements it. Earth tells us about global signatures, isotope shifts, extinction patterns, chemical oddities in sediments. The Moon and Mars, with their slower surface turnover, offer the chance, however slim, of catching something more literal. A scar, a residue, a pattern. Together they frame a broader question. If technological civilizations arise often enough in cosmic history, not just here, but everywhere, then quiet, mostly dead worlds with long memories may be where their faintest echoes persist. Our nearest examples just happen to be in our own backyard. And if we want to test the Silurian hypothesis honestly, that backyard is part of the evidence. Not because we expect to find a fossil power plant in the next rover panorama, but because thinking carefully about off-world archives sharpens what we should expect, and what we shouldn't from the rocks beneath our own feet. Which brings us to the next step, how you would actually design a scientific test for any of this, without just cherry-picking convenient coincidences and calling them proof. If you want to move from fun idea to testable hypothesis, you have to do something very un-YouTube. You have to be prepared to be wrong. That's where scientists start, not with a story they like, but with a list of things that would convince them the story is false. Then they ask what kind of evidence would have to show up all at once in order to make the story worth taking seriously. For the Silurian hypothesis, that means thinking in bundles, not single clues. A lone carbon isotope shift could be natural, a spike in heavy metals. Volcanism, hydrothermal vents, weird local geology, soot in sediments. Wildfires have been burning landscapes since plants first came ashore. So you don't get excited by one signal, you look for several independent, that all line up in time. Imagine the expected bundle from an industrial civilization as a kind of musical chord in the rock record. First note, a rapid carbon isotope excursion. The kind that screams a lot of carbon moved from one reservoir to another very quickly. That's the warming part. Second note, anomalous metals. Copper, lead, nickel, rare earth elements, not just elevated, but elevated in ratios that match ore processing rather than ordinary volcanism. Think of the way our own industrial era has spiked lead and platinum group elements in recent sediments. Third note, combustion residues. Tiny black carbon particles and particular forms of soot that look like the output of high-temperature burning spread widely in marine and lake cores, not just next to some ancient wildfire. Fourth note, novel organics. Molecules that don't make sense as simple biological byproducts. Long-lived halogenated compounds, odd fluorinated structures, or polymer fragments that resist breakdown. The kind of thing life is unlikely to invent by accident, but chemistry labs do all the time. Each of these on its own has plausible natural explanations. Together in the same narrow slice of time, on multiple continents, that's when eyebrows go up. But same slice of time is trickier than it sounds. Rocks don't come with printed dates, they come with layers. To say that a carbon shift in a deep sea core and a metal spike in a river delta are truly simultaneous, you need stratigraphic precision. This is where correlation comes in. Scientists match layers using global markers, known magnetic reversals in Earth's field, ash from dated volcanic eruptions, characteristic microfossils that lived only in certain windows of time, patterns of climate cycles written in the chemistry of the sediments. If the same magnetic flip, for example, sits just below an anomaly in cores from the Pacific, the Atlantic, and an ancient lake in what is now China, you can start to stitch those records together. You build a time grid. Then you ask, do the weird signals stack up in the same place on that grid within, say, a few tens of thousands of years? Or are you quietly sliding things around until they look impressive? This is where statistics and boredom enter the story. A honest test means defining your criteria before you go hunting. You write down a null hypothesis, any coincidences of carbon shifts, metals and organics, are due to known natural processes and random overlap. Then you ask, if that null hypothesis is true, how often would you expect to see bundles like the one you're proposing, purely by chance, across all the cores we've sampled? If the answer is pretty often, then your pattern isn't special. If the answer is almost never, and yet the pattern shows up, then the null hypothesis starts to wobble. Crucially, you don't get to notice an odd event first and then tailor the rules around it. That's the cherry-picking trap. You have to set your thresholds and your time windows in advance, and you have to apply them consistently, including to intervals where you don't expect to find anything. Both the boring and the interesting slices get treated the same. Even then, no evidence isn't as simple as it sounds. If we look at 3 ocean cores and don't find a Silurian-style bundle, that tells us almost nothing. If we systematically sample dozens of well-dated sequences from different environments and still don't see anything, we can start to say something stronger, but always relative to our detection limits. There are many ways for a signal to exist and still slip past us. It could be too small compared to natural background variability. It could be confined to coastal plains that have long since been subducted. It could be locked up in rocks we haven't drilled, or in cores that sit in warehouses, unanalyzed for the right compounds because nobody thought to look. So a responsible conclusion sounds more like, given the sections we've actually sampled, and the sensitivity of our methods, we can rule out a global industrial civilization with an impact equal to or greater than the modern Anthropocene during these specific time intervals. Not as dramatic, but much more honest. If you wanted to turn the Silurian hypothesis into a real research program, it would look surprisingly practical. First, you'd map out the best continuous sediment records from the past 500 million years, deep sea cores, undisturbed lake beds, epicontinental seas, places where mud has been quietly piling up for tens of millions of years. Second, you'd design a suite of measurements, carbon and nitrogen isotopes, trace metals, specific combustion markers, targeted scans for persistent synthetic-style organics, and apply them to those cores at relatively high resolution across key intervals. Not just the famous events like the PETM, but quieter stretches too. So you have a baseline for how natural variability looks. Third, you'd reopen the archives. Thousands of cores have already been drilled by scientific ocean drilling programs. Many have basic chemistry logged, but not the kind of detailed cross-proxy technosignature search the Silurian hypothesis calls for. You don't have to start from scratch. You can go back to stored samples and look again with new questions. Finally, you'd publish your criteria, your methods, and your negative results, so that any claimed hit can be weighed against the full data set, not just the weird bits. At the end of that process, you probably wouldn't have a fossil power plant. You'd have something quieter but more powerful, a clearer picture of what our own industrial fingerprint looks like in the language of rocks, and how loudly or how faintly it will speak to whoever or whatever reads Earth's history after we're gone. Which raises one last question. If our civilization's story is now written into the strata, what does that inscription say about how long we can expect to stay here? Before we follow that question any further down into the rock record, a quick note for those of you who like this kind of slow, careful mystery. If you're enjoying drifting off to deep time with this channel, we put together a book collecting 12 of the strangest, still unresolved puzzles in history and science. Not the clickbait kind, but the ones that remain genuinely open after experts have taken their best shot. You can find it on our website, there's a link in the description, and there's a discount on it this week if you happen to be listening while that's still running. If you do pick it up, treat it the same way we're treating the Silurian hypothesis here, as an invitation to think more clearly, not as proof that the universe is full of hidden puppet masters. Because mystery can mean very different things depending on who's using the word. On the internet, Mystery often means something we don't understand, therefore anything goes. A blurry photograph. A strange coincidence, a gap in a timeline. The story jumps straight from "we're not sure" to "it must be aliens" or lost civilizations or secret technologies beyond anything we can imagine. In science, mystery means something much narrower and in its own way more interesting. It means here is a pattern we can measure that doesn't yet fit comfortably inside our best current explanations. That's all. No hidden agenda, no guaranteed drama, just a mismatch between model and reality that refuses to go away when you poke it. Real mysteries come with boundaries. They live in data sets you can reanalyze, in fossils you can re-examine, in experiments you can repeat. They are framed by what we already know and by how sure we are of that knowledge. When paleontologists say, "we don't yet know exactly why the Neanderthals disappeared," they are not secretly throwing open the door to time travelers. They are saying, given the dates we have, and the climate reconstructions, and the genetic evidence, several mechanisms remain plausible, and we don't have enough resolution to pick just one. Uncertainty in that sense is not ignorance. It's a carefully drawn map of where the light fades out. The Silurian Hypothesis sits right on that boundary between internet myth and genuine unknown. On one side you have the familiar story. Maybe there was an advanced civilization hundreds of millions of years ago, wiped clean by time, leaving behind nothing but a few out-of-place artifacts and some suspicious rock formations. That version tends to skip the hard parts. Erosion, plate tectonics, the chemistry of sediments, the way random chance can generate things that look startlingly artificial. On the other side, you have the strictly geological question we've been following. If an industrial civilization did exist deep in the past, what kind of signal would it leave in the rocks, and would we even notice? Framed that way, it stops being a conspiracy theory and turns into a test. Notice how modest the claim actually is. We are not saying there was a civilization in the Silurian, and the evidence proves it. We are not even saying there was probably some kind of civilization back then. The answer, given everything we know, is still probably not. No obvious technosignatures have turned up in well-studied intervals. The chemistry of past climate events, as far as we can tell, looks explainable in terms of volcanic outgassing, orbital cycles and feedbacks in the carbon cycle. The fossil record shows no clear candidates for species that were building cities and factories. But probably not is not the same as impossible, and that small gap between them is where the hypothesis earns its keep. Because to say probably not responsibly, you have to define what yes would have looked like. You have to build that whole framework of expected bundles, detection limits, and sampling strategies. You have to think hard about how Earth edits its own memory, which parts of the crust get recycled, and how easily our own distinctive footprint could be blurred into something that looks natural. In doing that, you learn a great deal about the one industrial civilization we do know exists. Us. When you ask, could we detect a civilization like ours 100 million years from now? You're also asking quietly, how long does our mark on the planet actually last? How loud is our signal, and how fast does it fade? You're forced to think in units that are very different from election cycles or human lifespans. Instead of worrying about next year's economy, you're tracing the arc of carbon emissions through thousands of future monsoons, or imagining our landfills compacted into thin, plastic-rich seams in some future cliff face. The Silurian Hypothesis in that sense is a mirror. We hold up an imaginary ancient civilization not because we expect to find it, but to see our own world more clearly. If it turns out that an Anthropocene-level technosignature would be hard to spot after a few 100 million years, that tells us something sobering about how fragile the evidence for complex life is. A whole planetary experiment in industry and electricity reduced to a thin chemical smudge. If, on the other hand, our signal looks likely to endure, etched into multiple archives around the globe, that tells us something else just as sobering, we are changing the planet in ways that future geologists, human or otherwise, will not be able to miss. Either way, the question loops back to us. We started this journey by wondering whether someone might have come before. The next step is to turn that question around and ask what our own geological story says about how long a civilization like ours can last, and what kind of inheritance it leaves behind. To answer that, we have to leave the ancient hypothetical Silurians where they belong, as a useful thought experiment, and focus on the one case that isn't hypothetical at all. Us right now writing our chapter into the stone. So let's stay with us for a while. Imagine a future stratigrapher sifting through a core of mud that used to be the floor of our ocean. They're living maybe 10 million years from now. Maybe they're human descendants, maybe they're something else entirely, looking back at a world they never knew. What do they see when their measurements reach our layer? The first thing that hits them probably isn't plastic or skyscrapers turned to dust. It's chemistry. There's a sharp, skinny spike in light carbon isotopes, the sort we've pumped into the air by burning fossil fuels. It looks similar to some past events they already know about, the Paleocene-Eocene Thermal Maximum, for instance, but steeper, faster. In geological terms, it goes almost straight up and down. A few tens of thousands of years, perhaps less compared to the hundreds of thousands that older natural events tend to take. Layered on top of that, they might pick up strange patterns in nitrogen. Our fertilizers, washed off fields and into rivers, then out to the sea, leave a telltale signature when plankton bloom, die and fall. Too much nitrogen too fast creates dead zones. The sediments below those zones carry the imprint of low oxygen and altered nitrogen cycling. It's another little flag, next to the carbon one, saying, something pushed these systems out of balance. In the same slice of rock, species start to thin out. Microfossils that were common suddenly disappear or shrink in diversity. Larger animals leave a more patchy record. On land, where the archive is always more fragmentary, you might still notice a familiar pattern. Megafauna dropping out, ranges collapsing, a burst of extinctions that hits multiple habitats at once. None of those pieces by themselves scream cities and smartphones. Volcanoes can cause rapid warming. Methane releases from seafloor sediments can distort carbon isotopes. Natural nutrient pulses can trigger eutrophication. Extinctions happen, but taken together as a bundle, our moment in time starts to look odd. The carbon spike is unusually sharp. The nitrogen anomalies are global and sustained. The extinction pattern is skewed toward large animals and certain ecological niches in a way that looks targeted, not random. Tiny traces of synthetic molecules, halogenated compounds, complex fluorocarbons, might still be detectable in places that have stayed cool and buried. Heavy metals like lead, chromium, and rare earth elements might show a sudden coordinated rise, then a long, slow decay. From a distance of millions of years, all of that compresses down. Our modern world shrinks to a smear a few centimeters thick. Empires, wars, social media, all the noise of daily life, vanish into a single tight package of anomalies. To that future geologist, our presence would look like a brief, intense perturbation. A pulse. Something, some set of processes operated for a geological instant, rewired the surface systems of the planet, and then either calmed down or vanished. Would they know it was us? Would they know it was industry? Maybe. They might infer some kind of combustion-based energy system from the scale and pace of carbon release. They might suspect widespread artificial fixation of nitrogen, simply because natural sources struggle to produce that much fertilizer that quickly on every continent at once. If exotic molecules survive in enough places, they might be able to say, with some confidence, this layer contains compounds that almost certainly required deliberate synthesis. But even then, their picture of us would be blunt, pixelated. They'd know there had been a civilization, in the sense of an agent that could rearrange global cycles, but not its myths, its languages, its mistakes, and small kindnesses. That difference between rocks remember and stories remember is where the Silurian hypothesis becomes less about aliens in the past and more about how we think of our own future. Geology is durable. A shift in carbon isotopes, once buried and preserved, can outlast continents. But archives of meaning, libraries, hard drives, cloud servers humming in data centers are fragile. They depend on power grids, on institutions, on someone caring enough to maintain and copy them. Lose that chain of custody for a few centuries, and the code might as well never have been written. From a deep time perspective, we've been very good at changing the chemistry of Earth, and not nearly as good at guaranteeing the survival of our knowledge about why and how we did it. The Silurian exercise flips that on its head. When we ask, why can't we see a civilization in the Silurian rocks? We're also asking, why would anyone see us? And the answer seems to be, they might, but only in certain ways. We are geologically loud in carbon, loud in nitrogen, loud in the pattern of extinctions and ecosystem shifts. We are quieter in direct artifacts, quieter still in the long-term survival of our own self-understanding. That has an uncomfortable implication for our longevity. If civilizations mostly show up as brief pulses, if the rock record compresses tens of thousands of years of turbulence into a smudge, then perhaps long-lived, stable technospheres are rare. Maybe the usual pattern is rapid rise, planetary scale experiment, then either collapse or radical transformation into something that leaves a much softer mark. We don't know. We can't know yet. Our sample size is 1. But thinking in these terms nudges us toward different questions. Not just, can we keep the lights on for another century? But what kind of signal do we want to leave in the rocks, and for how long? If our industrial phase is a one-off flash, we've already guaranteed that future geologists will notice it. The carbon and nitrogen pulses are baked in. What's still under our control is everything that comes after the spike. Do we allow the extinction pattern to bite deep, reshaping the tree of life for tens of millions of years? Do we let our brief moment close out as a mass extinction cliff? Or do we find a way to taper the curve to become a civilization that can ride out of its own disturbance? You don't have to believe in lost Silurian cities to feel the weight of that choice. The hypothesis doesn't scold. It just stretches our timeline so far that short-term arguments start to look small, provincial, a little bit silly. From that height, stewardship isn't about purity or guilt. It's about editing, about deciding, consciously, what kind of chapter we want our species to write into the stone. Will we be a thin, sharp line, sudden warming, poisoned oceans, a knot of extinctions and then silence? Or can we imagine a different stratigraphic story? One where the initial shock is followed not by collapse but by stabilization, adaptation, maybe even a long, slow, sustainable presence that blurs into the background hum of Earth's own rhythms. The Silurian hypothesis doesn't answer that. It can't. What it does, quietly, is remind us that detectability is limited but not zero. If someone were looking for us in some far future core lab, they would find something. A planet that, for a moment, woke up and rearranged itself. What happens next, whether that rearrangement becomes a transient scar or the first line of a much longer story, is the part we're still writing. Given everything we've just walked through, the most honest answer is probably not the way we usually picture it. If by civilization you mean something like ours, global industry, long-distance trade, dense cities, a species capable of changing carbon, nitrogen and metal cycles all at once, then the rocks are, so far, pretty quiet. We don't see repeated patterns of our particular kind of disturbance. No earlier, sharp, industrial-style carbon pulse with the same fingerprint. No layered stack of synthetic molecules that seem to come and go on 100,000-year intervals. No geochemical chorus of combustion, fertilizer, heavy metals and complex pollutants that clearly isn't just volcanoes or microbes doing what they always do. That doesn't mean it's impossible. It means that if something like that happened, it was either very brief, very localized, very different in its energy sources, or it has been mostly edited away by time. Because a lot would vanish. Skyscrapers, roads, bridges, airplanes, ships, gone. Ground down, subducted, metamorphosed into anonymous grains. Buried data centers and underground malls wouldn't fare much better over a few million years, let alone a few 100 million. Forests erase cities quickly, even on human timescales. Plate tectonics and erosion simply finish the job. Books, paintings, music, digital archives, all of that is ephemeral. Clay tablets from a few thousand years ago are already hard to read. Imagine trying to find a USB stick from the Triassic and expecting it to work. Individual artifacts are the least reliable witness. What might survive, for us or for anyone before us, is the quiet, stubborn stuff, chemistry and patterns. Carbon isotopes shifted abruptly, out of sync with known orbital cycles. Nitrogen and phosphorus anomalies hinting at fertilization on a planetary scale. Sudden changes in sediment grain size or composition that point to widespread land clearance and soil erosion. Heavy metals and rare elements showing coordinated spikes that don't match known ore deposits or natural weathering. Synthetic molecules with no plausible natural pathway might linger here and there, trapped in anoxic muds, Antarctic ice, deep-sea clays. Not a full catalogue, just ghosts. A few odd fluorinated chains. A weird halo of long-lived plastics turned waxy and inert. Enough to say something non-biological was synthesizing complex stuff here, but not enough to reconstruct blueprints or brand names. And then there's biology. Extinction patterns that look selective rather than random. A sudden global pruning of large animals or certain marine groups. Rapid migrations in pollen and microfossils that imply whole biomes shifting faster than they usually do. These are the kinds of things deep time can keep. So when we ask whether there was a civilization before humans, we're really weighing two facts against each other. On one side, Earth's record is brutally incomplete. It throws away coastlines, it recycles seafloors. Whole continents' worth of shallow deposits disappear into subduction zones and mountain belts. The further back you go, the patchier everything gets. Asking the Silurian rocks to faithfully preserve a few thousand years of cities is like asking an old worn-through book to still show every original pencil note in the margins. On the other side, global anomalies are surprisingly persistent. If something large-scale disturbed the carbon cycle, rewired nutrient flows and altered ecosystems all over the planet, there is a good chance some trace of that disturbance would survive. Not everywhere, not clearly, but in enough scattered cores and outcrops that a pattern could eventually be pieced together. Right now, we don't see an earlier pattern that we need civilization to explain. The big events we do know, the PETM, ocean and Anoxic events, classic mass extinctions, can be accounted for with known natural processes. They're dramatic, but they don't need factories. That doesn't close the door. It just means the default explanation stays boring until the rocks force us to be more imaginative. And that, in the end, is the real value of the Silurian hypothesis. It's not proof of anything hidden. It's a disciplined way to think about what we'd expect to find, how we'd tell natural and artificial signals apart, and where our own story fits into the much longer rhythm of the planet. It reminds us that our knowledge is provisional, that new cores and new techniques can always surprise us. But it also reassures us that Earth does keep some secrets, especially the big ones, written softly but legibly in mud and stone. As you settle into sleep, you can imagine those layers: ancient seas, buried forests, vanished rivers. Each one holding a thin, fragile trace of worlds that felt permanent while they were alive, and are now compressed into a few millimeters of rock. Our layer is one of those, bright, noisy, full of signals that will someday be quiet. Above it, there will be others we can't yet imagine. Below it, there are chapters we only glimpse in tiny fragments. Between them all runs the same question: who was here, and how would we know? If your eyes are getting heavy now, let that question fade into the background like distant surf. Deep time will keep ticking, whether we watch it or not. The planet will go on layering memories over our own, folding us gently into its long, slow archive of mysteries. If you've enjoyed drifting through that archive tonight, take a moment, before you nod off, to tap like and to subscribe so you don't miss the next journey through lost ages. Leave a comment telling us where you're listening from. It's always fascinating to see this little community scattered across the modern world, sharing stories about ancient ones. And if you'd like to explore further, we've put together a book on 12 prehistoric secrets, deep time puzzles and turning points that shaped the world long before recorded history. You can read more about it or pick up a copy on our website. The link is waiting for you in the description. For now, though, you can let the questions rest. Somewhere far below your feet, the rocks are keeping watch,